We'll start coming up. No, start telling the people to come up. And tell Natasha to tell them as well. We're going to be late. Because they're going to see him. Hey. Hey, 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 hey. Hey, 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 hey. Hey, 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 hey. Hey, 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 hey. Hey, 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 hey. Wow. Everyone must. How's it going, bro? You right? Everyone must have been like, "What a bitch!" How's it going? You right? How's it going? You okay? Thanks for coming back. So he was a good presenter then, if you guys are back. How's it going, Dana? Guys, if you can help us out and come to the front, sorry, so that people that are late can just sit at the back. Thanks a lot. Really appreciate that. Oh, Dana, I wanted you on the spotlight there. So, gents, one thing I did want to mention, Barry, one thing I did want to mention is that we're going to be live streaming this exactly at 9:30. So if you guys want to get the code, just to send it out to friends that can actually see it, they're more than welcome to, that couldn't actually be here. So whoever did want to see it. Yeah, it's all good. Hello. So out of curiosity, has everyone read the sign over there? Yeah. Okay. All right, thank you. There is empty beer bottles that will get thrown at you. Barry?
Any sound engineer in the room?
So when I say Barry, he's mixing. All right, well, thank you very much for coming out. Really appreciate your time spending it with us. Specifically, today's introduction is on the more advanced. So yesterday we were talking about basics of wireless, what's the spectrum, how all that's working. Now we're taking it to the next level of introducing phenomenal new technology that just got released, which I believe truly is going to be the new cornerstone into technology. I'd like to present Andrea, who's the applications engineer at Shure as well, along with Barry. Today we're going to be specifically talking about this bad boy. And as I said, it's a phenomenal new product that's going to really make waves in the industry. whoever has experience with the Axient system, that's got phenomenal, range and a lot of really good press over the last couple of years. But this one really takes it to the next level. So without further ado, I'd like to introduce Mr. Andrea from Shure.
Good morning, everybody. I'm kind of tired and a little bit jet lagged because yesterday morning I was walking in Venice Beach in Los Angeles waiting for my flight coming back from NAB. I'm not just telling you this thing because I was having a nice vacation, but because I was in Vegas where Shure presented finally in public for the first time the new Shure Axient Digital. And I'm very happy that I can finally speak freely about it. So, it will take a little time to get there. Before, I'd like to ask you, what are your questions about digital wireless, state of the art of the technology nowadays? What are your expectations from this training and from these new technologies? And how do you see the present and the future? Yesterday, I think Barry spoke quite a lot about the spectrum allocation. Coming back from US, it looks like we are in heaven in terms of RF, because running a scan over there and finding space for 5 wireless microphones is a challenge. Here, we are not at that point for several reasons. One of them is that we don't have digital TV, digital terrestrial TV. So the TV is not working on the UHF band, but nevertheless, our shows are as complicated as the shows in US. It means many channels, LED screens, and other sources of interferences around, and the same tolerance for failure. That's exactly no tolerance. So if you don't mind, I would like to start with your questions, and then perhaps it will help me to understand where the training has to go before we enter in details into the new boy over there. Hey guys, not all together, please. I know you have a question. Okay.
With the digital systems, is it possible to run multiple microphones on the one carrier frequency?
Okay. I knew it. So, multiple microphones on one carrier. Then, this is the only question you have about wireless digital? So 8 years of research from R&D department, a lot of engineering chat to tell you, so you're not interested in this. If you ask the price, you have to ask Dino, probably better than me, but it will be around UHF for the AD version. And this is the only time perhaps I will mention the price one more time, and that's it. Okay, while you think your question, if you're shy, you can write it down during the day. We can start with a refresh of some very basic concepts that I'm sure everybody in the room already knows. So what is a modulation scheme? Yesterday you probably spoke about spectrum, about waves. Obviously, to carry information, we need a wave to be modulated, and it can be modulated in different time, in different ways: amplitude, frequency, phase, And obviously, we can transfer through VRF an analog signal, so it's somehow something related to our audio signal, or a data stream, 0 and 1. That's what we get at the output of a digital converter. So you already spoke yesterday about amplitude modulation, frequency modulation, or phase modulation in the analog world. This is how they look like. And perhaps you already spoke about the difference of the different behaviors from analog and digital carriers. An analog carrier looks like this in the spectrum analyzer when there is no noise. We have a spectrum analyzer, so later on we'll play a little bit around it to see exactly what are the difference between analog transmitters and digital transmitters. And this is a modulated carrier. So the audio is added to the frequency of a carrier, and it has a deviation that is 200 kilohertz. This number, 200 kilohertz, is given us by FCC mainly, that's the American Regulation Authority, and some other adopted it, so it became a standard. It's the deviation that any wireless microphone can have. This was having several impacts on our transmitters and on our receivers. I mean, if you ever used Accent or UHFR or any competitors, they sound good, but they have limits. The two limits are the frequency response and the dynamic range. These limits are somehow related to this deviation limit. So we cannot have an 1 megahertz deviation, and this means that the amount of dynamic range that we could carry over RF, it was about 50 dB. This was the reason why in the analog transmitters, we had a compressor at the transmitter and an expander at the receiver. For similar reasons, the maximum dynamic range, the maximum frequency response couldn't go from 20 hertz to 20 kilohertz because the very low frequencies were very difficult to modulate. So most of the microphones are having an high-pass filter around 50, 60 hertz. But for most of the application, more than okay. If we have a vocal microphone, we don't really care about the 25 hertz. And most probably not even if we have a bass, actually. But it's something that was affecting the phase response too. So we had to do some processing in the analog stage. And to make this processing good, we needed money. So to build a good analog wireless microphone, there was the need of a lot of analog processing that was costing quite a lot. This was the main limit. Talking with our engineers in Chicago, I discovered a lot of things. Mostly, obviously, the components that manufacturers are using are components available for everyone in the market. And the choice of a component is based on the tolerance we can accept. So having a tolerance of 0.1 dB was by far more expensive than having a tolerance of 3 dB. So this is one of the differences between the different analog systems. In digital, it works slightly different. So what are the ways we use to modulate the carriers and to carry information over RF? One is called amplitude shift gain. We modulate the amplitude. If we have to send a 0, the amplitude will be at a certain level. If we want to send out a 1, it will be at a different level. Actually, as the amplitude modulation is just for you to know, because we don't really use this modulation scheme in professional audio. Then there is frequency shift gain, or the audio signal bit stream modulates the frequency of a carrier signal, as it happens for the frequency modulation. and this is implemented in mainly in 2.4 gigahertz product like GLXD or. And then there is the phase shift gain. Phase shift gain is the way used the modulation used for the microphone I'm using now. It's just switching the phase, can be with 4.
With the frequency shift key, do you have a 0, 1 frequency and a 1 a different frequency and just swap between the two frequencies?
No, not really.
No.
Okay, good question anyway. So, something I had to say before. What I'm describing now is not exactly what's happening. This is a simplified version. Because if we go into details, we can stay here speaking for days about mathematics. And anyway, no. The frequency shift key in, there are 2 slightly different frequencies. One is sending a certain, actually there are 4 different frequencies. And everyone is sending out a couple of bits. So 00, 01, 10, 11. To aggregate more information, we never send out 1 bit per time, even also because it would be very difficult for the receiver to understand the timing of it. So we always send at least 2 bits per time. So out of 4 combinations, the frequency changes according to the different couple of bits. Same for the phase shift gain. We have 4 different points, 4 different angles for the phase, and it changes accordingly to the different couple of bits. And then there is a system called QAM16 or QAM32 or QAM8. That's a combination of phase shift gain and amplitude shift gain. That's what is used in the, let's say, high-tier digital systems. Now, when I got introduced to it, my question was, okay, what Accent Digital is using? Accent Digital is not using any of these traditional modulation schematics. It's using a combination of QAM16 with different treatment, and it's using PSK and ASK to transfer different kinds of bits. So one is the main bits are the clock and the audio, and the other bits are used for all the other informations that are not really vital. And we will see in details why, I mean, this is just an introduction. We will see in details how it works and what's changing in our daily workflow because of these things happening in the background. This is how they look like into a spectrum analyzer. Now, phase shift gain is working with very high frequencies pretty well, but in the UHF band is by far not enough efficient. And phase shift gain is a good system to transfer data with a good reliability. And obviously, the system they adopted for Accent is considered superior in terms of complexity and in terms of reliability. One of the major things is the spectrum efficiency when we talk about digital wireless. Now, what do I mean with spectrum efficiency? The number of channels that we can have on air at the same time. This is one of, I'd say, 4 major benefits of digital wireless. We are considering a very efficient analog system, UHFR, and is able to have up to 12 channels on air on one TV channel, that is a space of 8 megahertz. With ULXD in the same space in high density mode, so losing something in terms of range, let's say the range is reduced by 50%, we can have up to 60 channels. With the new platform, we are able to have the same 60 plus channels in 8 megahertz with the same range of a traditional analog wireless system. So the amount of channels that we can have in the same space is much more, and the reason why is that the intermodulation distortion is not as relevant as it was before for analog systems. If we get two analog transmitters and we have them close to each other, they will produce spurious frequencies that will be disturbing other transmitters on the same frequency. While with the digital system, we don't have this issue that much, or we don't have this issue at all, according to the different systems and to the different powers of transmission. But the reason behind it is that we are just sending 0 and 1. So our components, all our system is much more deterministic, and we can say exactly at any point how much power the transmitter will be using, how much the RF amplifier will be operating. And for this reason, we can tune it in a way that it doesn't produce intermodulation distortion as an analog system was. We'll do some demonstrations about it. Clear? Fair enough? Yeah, this is what I was mentioning before. This presentation is pretty long, and I can't see the time to get inside the menus and the features of Accent Digital. So, as I was mentioning before, we are not transmitting 1 bit per time, we transmit several bits. And this is how the modulation scheme looks like. Another thing that can be considered relevant is that the level of noise introduced in the path from the transmitters to the receiver is very close to 0. While with any distortion happening in the journey was affecting the analog transmission, with the digital transmission this is not happening. At the 99%, we can say that if a signal goes through, is exactly the signal we sent from the transmitter. Otherwise, if a distortion or the interferences are too loud, the signal purely doesn't pass. This is how a modulation PSK4 looks like. And for who's more nerd, this is how QAM16 looks like. And for a super nerd inside the room, this is how a real 8PSK looks like with all the errors. This is a very important concept. As much as the challenge when Shure decided to do a new wireless system, they went to the engineers and they said, we would like a system that purely doesn't drop out in any case. And it was a kind of difficult challenge. Now, digging a little bit, obviously, everything else was not even mentioned, but audio has to be possibly perfect, and all the features have to be there. So one of the major limitations of this kind of modulation is the amount of possible error over time. And obviously, the bit error rate is increasing with RF noise. We don't have much here, but with all these microphones and in-ear monitors and error, there is a little bit of noise. Multipath, that's meaning reflections. Nonlinearity of RF circuits, or obviously low RF power. So when the transmitter is at the edge of a coverage area, the number of possible mistakes, possible error increases. So 8PSK would require moderate RF noise floor, not really a noisy environment. And 16 QAM, the traditional system, the one we can find on Wikipedia, the standard system, doesn't work very well in noisy environment. So the challenge was to build a new modulation scheme to create a system that was reliable and resilient in a noisy RF environments and able to cover an extended area. So a little bit balance between pros and cons from analog and digital. Definitely the major benefit is that we have a lot of spectral efficiency we didn't have before. We have a better audio. Better audio means that in the digital world, once the converter is a good converter and the preamplifier is a good preamplifier, the RF link is almost transparent. So we can send audio 20 hertz to 24 kilohertz, 24 bits of pure digital audio. And we saw improved RF performances because of these reasons. Plus, we are now able to encrypt a signal, thing that in analog was pretty hard to do. Now, if you are doing rock and roll, who cares about encryption? But if we are working on a corporate environment, if our customer is a bank or an important multinational company, they care about encryption. For Google or Facebook or every of these big corporate, it's mandatory that all their communications are encrypted. Then someone can still bribe the sound engineer and get a USB stick of a convention eventually, but that would be a little more dangerous. What's changing? What do we trade for these benefits? Is an increased complexity of a system, and as we will start digging into the menus, we will see that there are many more settings available. We can still be confident, switch on, sync the transmitter, it works, but we can actually decide many more things than before in our RF system. And latency. In the last 15, 17 years, digital consoles are a must. Everybody's using it. Processors of any kind, and probably the last kind of equipment that became digital is the wireless microphone. The main reason why, I would say, is the latency. And just to balance all this number, we have Ariana Grande here. Not just because she is cute, but the picture was pretty helpful. She's having a microphone in her hands, she's singing. The signal from the microphone, that's I think a UR2, the signal from the microphone goes to the receiver. At that time, UHFR, no latency, or 0.09 milliseconds, whatever. But we can consider it as 0. And then it was passing through a converter, entering a digital console, doing whatever, plugins and whatever, and after a few milliseconds, it was going back to her in-ear monitors. Now, the voice in her in-ear monitors were combined with the voice, with the real voice, the direct sound going from the mouth and mainly through the bones. Adding too much latency in this process would give her an uncomfortable sensation, as probably she's the one paying the bills for all the technicians involved in the tour. We don't want her to be uncomfortable. So we can consider that from 0 to 3 milliseconds latency is there. We can measure it, but it's not heard and perceived in any way from a human, a normal human at least. Violin players and classic musicians are not considered normal humans. So from 3 to 5 milliseconds, it can be noticed, but somehow our brain is able to perceive it as a single sound. So from 5 to 15 milliseconds starts to be disturbing at different points for every one of us. I'm practically deaf, so for me, 7, 8 milliseconds is not a big deal. I can talk and I can sing even without latency, so that's not an issue. But probably if you are playing a guitar or if you are really singing, it's disturbing, while if you are giving a speech, it's something you can manage. And more than 15 milliseconds in general is the moment where our brain starts perceiving two separate sounds. So the second one is perceived as an echo. And obviously, we should keep this latency as short as possible. So when Shure went to the engineering department, ordering them to provide a new wireless system, latency was one of our concerns. ULXD was having about 2.9 milliseconds of latency. That was considered good for most of the applications. So I really rarely heard about complaints or something. The only time that's happened is with a violin player, with in-ear monitors. For her, it was kind of too much. The problem were not just the 3 milliseconds of ULXD. The problems were the 3 milliseconds of ULXD, and on top of it, the latency of a console and of all the network, or whatever it was. Then back to the in-ear monitors, it was reaching and perhaps going over 5 milliseconds. So this was considered disturbing. So we have now another nice slide with some comparisons between analog and digital modulation. We can get quickly through it. When we are close to the end of a range, the audio can get noisy because we don't have a good signal-to-noise ratio with analog system, but it's still there. In the digital world, it's more 0-1, so the clear audio is there, and then there is a dropout. This was another matter of concerns for our engineering department, because obviously we have RF indicators in the receivers, so we know how much power the receiver is getting, but somehow it was not helping. So a new indicator has been added to tell the engineers, you're fine, you still have audio, but we are not so fine, and then before the silence happens. The bandwidth used by an analog modulation changes according to the signal. The deviation is different. We can actually see it probably. Whoop. So if I switch on okay, now it should be on. Frequency 536 megahertz. And we reduce the span. Okay, if we see, this is my transmitter. If I move it, it changes. So yeah, it's him. We can see that there is a carrier. These two spikes are used for the squelch. and you have these spurious frequencies. As we get close with another transmitter, the spurious frequencies are the one combining each other and giving us intermodulation. But as you see with the audio, the bandwidth increase. This is not happening if we do the same thing with the digital system. With the digital system, doesn't matter if there is audio or not, and we can bring my transmitter. If I can see the frequency, 6 to 8 megahertz. As you can see, that I speak or not, 0 and 1 are always there. So if there is silence, it's not that the digital audio signal is 0, 0, 0, 0. So this bandwidth is more predictable. And this is making possible to have transmitters in a kind of grill. When I got hired by Shure, the first question, I think the first question in an interview was, I have 3 transmitters, 601, 602, and 603 megahertz. Are they working? Is it right? No, because they produce intermodulation. So they cannot be on a regular spacing. They need to be spaced. If you do a frequency coordination, or if you see the groups inside an analog system, they will be always 604.2.275 or 605. I don't know what. Because the spacing cannot be regular. With a digital system, the grill can be regular. So we can have equidistant carriers that's making our frequency coordination more easy and more efficient. Audio frequency range, as we mentioned before, in analog is limited, while digital, after the converter, so we are talking about the RF link, is 20 hertz, 20 kilohertz without any limitation. The dynamic range, again, not the dynamic range of a wireless microphone, but the dynamic range of the RF link in analog is 50 dB, while in digital is easily up to 120 dBs. That's a 24-bit. Identification, obviously, we used to send information together with the carrier, but we couldn't really identify every transmitter. So if I have 2 accent analog transmitters over there, if I tune them at the same frequency, they are sending out exactly the same information. While with the digital modulation, we added the possibility for the receiver to understand what transmitter is operating. And this has an impact on our workflow again. We already spoke about encryption, and we already spoke about latency. I think also this part was already treated yesterday, but we go through it very, very quickly. So analog or digital, amplitude modulation, phase shift keying, whatever you like. What's the best spectrum to use? It's still UHF TV bands. So what we are used to have, what's going to perhaps to disappear in the next 10 or 20 years, today is still the best thing. Sometimes I heard people confusing 2.4 gigahertz or 1.8 gigahertz as a digital modulation. The two things are not related. These systems, ULXD as Axin Digital, are still working on the UHF band. In the Emirates here, the band allowed is from 470 megahertz up to 694. With some special license, we can still operate something in the 700 megahertz, while the 800 megahertz is not even sold as a special license because it's already occupied in the majority of the areas, of the urban areas, by mobile devices operators. But we still need spectrum to operate, and we still need UHF spectrum to operate. We can't get rid of it. There are products that are not working in the UHF band, 1.8, 2.4 gigahertz, but for what's the scope of our training today and what's probably your daily business, they are not good enough. On 2.4 gigahertz, we have to coexist together with the Wi-Fi, and this is a kind of unpredictable environment. So the amount of channels on air in 2.4 gigahertz is kind of limited. We can have theoretically 16, 18 channels. If we are not inside a laboratory, most probably the maximum number with the most advanced equipment is around 10, 12 channels. And in real life, often is much less. And as it's so unpredictable, we can't really trust it for professional use. 1.8 gigahertz is another portion of spectrum that can be used. It's free of license worldwide. It's called DECT. The problem is that you need to comply to a kind of old technology that's introducing 17, 18 milliseconds of latency, making it useless for the majority of sound reinforcement and definitely for every musical application. Sorry. So what can go wrong in our transmission, and what are the issues we can face? Interferences and intermodulations when we talk about analog. So these are our sources of interferences. All these things can be easily found on a stage.
Do you get any interference from the DSP and the actual microphone? You've got audio DSP interference from the physical equipment?
No, because it's already considered. So when they, yeah, it's built in first. Second thing, it's not having a real DSP inside. There is not a real DSP as a processor for a computer, and the amount of power involved is very, very limited. So it's not disturbing the transmission, but no. And as far as I know, there is no. It's not a matter of concern. Even having different system mixed and matched doesn't really produce any kind. I mean, it's not a strong one, but a lighting console on top of a receiver, yes, it can be. The major concern are LED screens. And yeah, this is how they look like. So different spikes moving around and increasing our noise floor, making a little more difficult our coordination. These lines are not consistent. They are not always there. They change according to the colors, the picture, and the format, the video format they are transmitting. So this makes our stages, our events a little more noisy in terms of RF, since we started to deal with big LED screens. And again, we spoke about intermodulation products. With 7 frequencies, we have up to 42 relevant intermodulation products. So this is one of the reasons why we need to do a frequency coordination with our analog systems. It's not that with digital we can purely ignore frequency coordination, but there is much more tolerance than before. And we have multipath interferences. So how multipath interferences are still there in analog or in digital, and the manufacturers found different ways to deal with it. The first one is called predictive antenna switching diversity. What it does is to get two signals from the two antennas we are used to connect to our systems. As soon, let's say that antenna A is the one in use, as soon as the comparator sees the antenna A going down and antenna B going up, it will switch from one to the other. So if you look at a ULXD transmitter, you can clearly see that here, if I tune it in the same range, so you can see 628, 050. We have only one line of orange LED, and only one of the two antennas is working per time, so one blue LED. The blue LED is telling us which antenna is working, and the orange LEDs are telling us how much energy we have. Then there are the more traditional analog systems. So two lines, in two independent lines, transforming the RF into audio, whatever it means, with intermediate frequency and demodulation and blah, blah, blah. And then an audio switch saying, okay, antenna A is giving me a better audio than antenna B. I switch on antenna A or antenna B. A little more complicated is when we have, instead of a switch, a combiner. It works as it used to work as we are used with the pump pot of a mixer. So according to A and B are good, okay, I keep them both, and I have a better signal-to-noise ratio. B is not good, I move towards A, but without a complete switching. This is the way UHFR is working, or Accent is working. And wideband tuning range or not. Most of our systems, except Accent, are having a tuning range of 60 megahertz. That's not a wide tuning range. There were reasons behind it. So obviously, if we have a wide tuning range, we can easily deal with different regulations, and we can use more spectrum. While with a narrow band, we have less frequencies to choose from. And from an inventory point of view, if you have all your microphones that are in the same frequency band, it's more easy than if you have to deal with separate frequency band. For who is familiar with the Shure frequency bands, we had a higher level of complication with the naming of the frequency bands. For me to learn them, it took 1 year, and I deal with wireless microphones, I'd say almost only with wireless microphones every day. H4E, G56, G5, so different models, different letters. Obviously, having a wideband system would help from this perspective. That's like, okay, I have an A receiver that is 470, 700 or 630 or whatever, would help. From a manufacturing perspective, and at the end, from a price perspective, having a wideband design costs more. Or, if it doesn't cost more, you have to trade somewhere. And what you trade to have a wide tuning range is that you can have less channels on air at the end of the day. So some manufacturers decided to have a very wide tuning range, but they had to compromise on the front-end filter. The front-end filter is the very first thing in an RF circuitry, excluding all the frequencies far from the interesting one, from the narrow tuning range we are interested. So to have more efficiency, we needed to make more narrow our tuning range. So Shure thought that 60 megahertz was a good compromise. Then in the Exient world, they had a wide tuning range, 220 plus megahertz. But again, there was somehow a trade-off, and the tuning range of the transmitters was still limited to 60 megahertz. With Exient Digital, they found a way to have a good front-end tuning filter, because all the platform is digital and software controlled, and there is many more things happening in the software part than in the hardware part. And they were able to have a wideband tuning system with a high efficiency. Now, I don't know if it's ever happened to you, but it happens to me very often. Someone gets a new wireless system, then they call me, and the first question is, okay, how can I increase the power? Thinking that increasing the power is automatically increasing the coverage area and the reliability and the safety of a system. So someone wants, I have 50 milliwatt, I have 100 milliwatt, I have 250 milliwatt. Actually, there is a relation, obviously, between coverage area and output power, but the output power mentioned in the settings is a nominal output power. So we can see with the analyzer how much does it change between 10 milliwatt and 50 milliwatts for our antennas. And sometimes, at least, in most cases, I would say, increasing the power, we add more reflections, making more difficult for our receiver to understand what's the good signal and what's the reflection. There are other ways to extend the coverage area. Obviously, from a manufacturer perspective, select a better modulation scheme and having more efficient antennas, or from a technician perspective, placing the antenna properly, using good cables, possibly super short cables, and having a system that performs in the best way. Receiver sensitivity setting, it's something we can work on. Sorry, this is going alone by itself. And with digital system, we can work on the algorithm that's correcting the errors we were seeing before to get more coverage. So even if our system is very far, and do you remember the red dots? The red dots out of our interesting area are becoming a little more. There are correction codes into any digital system to recover these errors. So if we have a better algorithm, we have more coverage, but it's not exactly only the power that gives us the coverage area. So if we want to increase the coverage area by 6 dB, if we want to increase our signal by 6 dB, we need to add 40 milliwatts to a system that's having 10 milliwatt of output power. And at the end, we get 7 dBm more in the transmission. That's equal probably to 10 to 20 meters at the very edge of a coverage area. But we lose a lot of efficiency. So with digitals, with digital systems, there is another thing that changed. The numbers now are different. If we compare, and we can actually do it, 10 milliwatt for Axient or UHFR, they are not behaving as the 10 milliwatt in a digital system. They will look like the 2 milliwatt for a digital system, perhaps. So the output power, and whenever you are selecting or just operating a wireless system, has not to be considered as a magic. If our system is not performing as we expect, most probably the mistake is somewhere else. It's not that we don't have enough power. Because even in low power mode, there is not much difference with the high power mode. To have a significant difference, we should go up to 100, perhaps 200 milliwatt, but in many countries it's purely not allowed or requires a special license. So the numbers of RF output power have to be considered really just as nominal numbers, but they don't really reflect the efficiency and the coverage area of a system. Now, before we enter into the Axient digital world, there is another part that I think it's very, very important. For whoever attended the training before, I used to spend 3 to 5 minutes talking about how to create a small network and to control through wireless workbench our wireless microphones. Today, I'd like to spend a little more time on this for 2 reasons. One is that there is more and more the need to be also network engineers, obviously not really network engineers, but to be IT oriented than before, because we deal with, I remember when I started working in late 90s, I didn't know what an IP address was. There was no RJ45 cables or connectors on a stage. And then they started to appear, and then in the last years I saw them more and more. And most of them were not really Ethernet protocol. They were purely cables transmitting something without IP addressing, without switches, without anything. And then we had the first networks on stage, and then finally I quit. And I said, okay, Kalas, I don't have to deal with it anymore. I joined Shure, and I had to deal with it much more than before. So if you agree, I would. And the other reason is that with Axient Digital, especially with Axient Digital, we have to use the network not only to control the system, but also to transport audio. Now, if the amount of information on a cable to control a system, the information going from wireless workbench to the receiver and vice versa, it was really few bits per hour, like nothing. If we are having 24, 48 channels on air, possibly with several nodes in a network, then we may need some more information to run a network and to troubleshoot what's going wrong. So I hope you don't mind if we spend, I'd say, 1 hour talking about networks, even if we are not network engineers, and I'm really the last one as a network engineer, but IT entered a lot our industry. And we took a lot of technologies from IT, and we have to deal with them. So some of this information are not really needed to set up a system, but if something goes wrong, it's pretty cool to know what can be the failure point, or how do we deal with it, how we can see the bandwidth really used by our channels, how we can reduce the stress of our network. And when we need to transport our audio over to different points, it's nice to know that there are efficient ways to do it and not non-efficient ways to do it. Now, if we have all the best network infrastructure, we may even don't care. Like, I have 25 gigabit switch, I can do whatever I like for as many channels as I want. But if we have a 1 megabit switch, that's kind of, 1 gigabit switch or 100 megabit switch, that's kind of different, and it can be really relevant to have an LT network, know what to do and how to troubleshoot, how to change the network for our needs. And as I was mentioning before, when we talk about digital audio, we do not talk anymore of real audio. We are transferring 0 and 1, and IT industry did it for years quite successfully. So we, as an audio industry, we stole their technology and we changed it a little bit, and we are using it. So this is a small summary of what I would like to discuss briefly. What are the concerns of analog? Why? I mean, analog is still there, and it will still be there, but compared to digital, it has some limitations. Very quickly, OSI model. Is anyone in the room aware of what an OSI model means? What is layer 2, layer 3 protocol? You are? You are. I'm looking. Okay. We'll talk a little bit about what is the hardware we use for a network. We will see what is the difference between speed and bandwidth. We will talk a little bit about timing or clocking. We will shortly see how to run a setup on Dante. Dante is one of the several protocols of digital audio, but I guess it's the most popular and most important, is used by our microphones. So for us, it's definitely the most important. Sorry. And a little bit of troubleshooting. When things go wrong, where do we look at? What do we do? How can we deal with it? So obviously, we are used to it. The analog is comfortable, reliable, easy to set up and to understand, well established. Everybody here knows perfectly what is an XLR, how it works, and it's still popular. while I was in Vegas a few days ago, I went to see a gig, Steely Dan, great, by the way. The console was still a very good analog, big 56 channels console. All the outboard was analog, the sound was great. So analog is there, and for some parts it will remain there. But same in Vegas, I saw for the very first time a boom stand, microphone stand, having an IP address. That was kind of exciting. So the microphone was connected with an XLR to the boom stand, and the boom stand was having a preamplifier and a converter sending out signal on RJ45 cable. So I'm not sure this will be the future. Perhaps we will have better places for the converter, but actually it's already there. I mean, most of our setups, we have an analog cable entering a box that's converting the signal and sending out 0 and 1, a big remote control with all the nice faders and lights, and then we convert back the signal at the latest possible stage, usually before the speakers, in the amplifiers, or if we have analog amplifiers, after the PA processor. We loved analog. I'm a big fan of analog, but still there are limitations. One cable, one signal. Multicore were heavy to run. I did it quite a lot. The routing was fixed. If I want to change the routing of an analog patch, I have to bring a cable and physically move it. It can accumulate noises, and it's very, very difficult to make redundant. So redundancy nowadays is a must. When we may speak for hours about the levels of redundancy available, but just to let you understand, as it was very difficult to create a redundant analog network, and for the Olympic Games, the networks, they have to be 4, 2 digital and 2 analogs. Out of every microphone, there was an analog splitter, and imagine it for 100 plus channels. An analog splitter sending out 2 channels. Then there was another analog splitter sending out to the converters and to the digital network other 2 channels. For the wireless microphones, they decided to go even more easily and having 4 receivers for every microphone to get the redundancy. So wired microphones were having several splitters, and wireless microphones were purely having several receivers. So it's kind of difficult to make an analog circuit redundant. And it's even more difficult to have this redundancy in automatic. So if I have 2 channels, even both of them are entering the mixer, how can I tell the mixer if the first one stops, move to another one? I can do it manually, but the time needed for an operator to do it is at least seconds. And while in analog, we can have redundant networks, and if I unplug an RJ45 cable, even if the operator is sleeping at the console, it will automatically swap to the secondary network, and it will continue working without anything noticeable from our perspective. So digital is reliable as analog, perhaps more, even if it's a little more tricky for us to set up, mainly because it's something relatively new in our industry. One cable can carry many channels, while an analog cable is carrying 1 channel, or a multicore, it's a lot of kgs going around. With an RJ45 cables, we can easily transport 500 channels. Not so easily, but we can. Cables are much lighter than before. and inexpensive, and in some cases can be relevant to think that we can use existing infrastructure. So if I have to install a new audio system in a big theater inside a casino in Las Vegas, because now I'm just back from Vegas, so I'm focusing on it. Most probably I won't find any XLR cable in the wall, but I will find a lot of fiber optic and Ethernet cables over there. I can share up to a certain level the network with other services. I'm much more flexible in routing. There is no noise, we can have redundancy, and whatever we have to do from an audio engineering perspective is to learn a little more about this technology. So digital signals, we can have obviously bits. 1 bit is 2 different states. 2 bit is 4 different states. 3 bit, we have 8 states. 4 bit, 16. These are the possibilities. This is the picture that I think everybody saw when someone starts teaching about digital audio. Now the funny thing is that this picture is wrong. This is not what's really happening. So we don't have a small stairs out of a analog to digital to analog converter. But it gives us an idea. Here we would have, it's I think a 8-bit signal. No, less than 8-bit, sorry. 4-bit signals. So not really proper, a good one for audio. We have 16 different levels. And this is what we call bit depth, that represent the amplitude of a signal. And then we have a sorry. And then we have a sample rate, that's the x-axis. How many times per second we take a picture of a signal to understand what's the level at a given point in time. And last, we need, here we have, yeah. And last, we need something to put every bit in the right time slot. That's what we call clock. These are the 3 major things when we talk about digital signals. So the bit rate, here it's explained quite well. And signal that is 24 bit at 48 kilohertz is using 1 megabit per second. That's the only number that I'd like you to remember, because it becomes useful when we build our networks. What is a digital protocol? Is a method of operation. Doesn't mean that is a standard. Actually, the major protocols are not standardized. And we have many different protocols. And here we have a list. You may be familiar with most of them. And ASCBU or SPDIF is the first one I was dealing with, at least. And as you can see, as we grow a little more in complexity, we immediately lose the bit rate and the amount of channels. So AVB, Dante, QLAN, Ravenna are layer 3 protocol. There is not a given amount of channels, and there is not a given bit rate, because it's kind of difficult to say in a Dante network to move, let's say, 500 channels, I need a certain amount of bandwidth. It depends how I build the network, how the receivers and the transmitters are connected, how many nodes or switches or whatever there is in between. But some other are more easy to manage and to manipulate. I'd say the most popular nowadays is the MADI. MADI can have up to 64 channels. Most of the time is actually 56. And the bit rate is 98 megabit per second. Connectors are standardized. MADI is a standard. While BlueLink is just for BSS devices. SuperMac and HyperMac are mainly used in Midas consoles, as far as I know. CobraNet and Ethersound have been their moments of popularity in the past. Nowadays, nobody is building a new system in CobraNet or even in Ethersound. The new systems are AVB, Dante, Ravenna. QLAN is a different kind of Dante for the QSys world. And here we enter the IT world. So try to imagine, when we talk about the layer, we can talk, I'd like you to imagine a Russian doll. So there is a first layer that is common to everyone, that is the transport layer. We need a cable to go from point A to point B. Doesn't matter how many channels, if it's bidirectional or not, we still have a physical connection between 2 points. Here, yeah, it's explained a little better. So I have a first 3 layers that I erased. They are not really relevant for us. And they are boxed together in the layer called transport. Then there is a layer called network. That's giving us the ability to connect the things in different ways. Before that, there is a data link. So, and we will see what's the level of intelligence required to transport data. So if in the layer 1 the system purely doesn't know, it should be reversed actually. Yeah, this way it's better. Layer 1 we have bits traveling. The second layer, it's giving us the data. So the data transmitted are somehow having information about where to go, where are they from. The layer 3 is a more precise information about it. Now let's see some real life example that makes by far more clear. A layer 1 network is a CD player connected in this case with a DSP or to a mixer. We have examples like ASCBU is a layer 1 protocol. So communication is single direction, and there is not much flexibility. I'm going from point A to point B. And it's called half duplex. If you're familiar with it, it's meaning that the signal can go just in one direction. As long as I'm transmitting from point A to point B, the network is busy. So I can pull another cable, or that's it. Another signal has to wait for my transmission to end. So let's say he is the receiver. Before he can reply, I have to stop speaking. Otherwise, the network is busy. And the basic infrastructure is just a repeater, what's called a hub. So the hub has no clue about what's happening in the network. It's without any kind of intelligence. It's just repeating many times what he receives. That's it. And this is what we call, so the hub is covering this part, but it has no idea about what's going on, who's transmitting the free old-style PC that are used here to show it, are having the knowledge, should have the knowledge of what's going on. So if instead of PCA, I have my stage box, on that particular cable, I will be able to send data only in one direction. Now, when I send data, I'm not meaning a channel. It's not that I send the TOM1 and then I send the TOM2. The data can be combined, so I can transport many channels on a single cable. But that's it. These are the problems related to layer 1 network. It's called one collision domain, meaning it's always meaning that the data are flowing just in one direction. If I am another part of a network, I have to wait that the network is free to send my information. So the amount of data is relatively small, and there is not much flexibility in terms of routing. I'd skip this part a little more. So data layer 2 is where we start to have a kind of knowledge. The infrastructure starts to have a knowledge about what's going on, who's transmitting where, what, and why. And in layer 2, we can see the introduction of the switches. After a few conversations, we were talking about layer 3 networks such as Dante, and one good point was, in our world, we don't really like real layer 3 networks, so having many things going on. We kind of like to have our audio protected from anything else, and layer 2 is the most used and the most popular way to use even layer 3 network in real world. An example, if I have a Dante stage box and my console, I don't want on the same cable or in the same network to have a light in console, right? So we keep our networks still a little bit close, but the possibility is already there. There are many things we can, I can connect to an Ethernet switch, the lighting console, and the audio at the same time. So to pass the data and to have this kind of intelligence, the switch uses MAC addresses. The MAC address, it's what we call media access control, and it's a unique address for every device. So not only for every device, for every network port on every and each device. It's a big number, and it's split in two different sections, as you can see in the example. The first 6 characters are vendor specific. Let's say my laptop is HP, so the first 6 characters are 38 EA A7, and every HP device in the world is having as MAC address these 6 characters, and then the second 6 are device specific. So my laptop will be the only one having 85, 77, 58, and every other laptop will have a different address. It's assigned by the manufacturer, so when I buy my laptop, it has this MAC address, and I can't change it. It's his physical address, its footprint. And this is what layer 2 uses to route the data. Now, without wasting too much of your time, I just want to briefly talk about the characteristics of a layer 2 network, and it's what we call usually a local area network. We can consider a local area network with devices in this room, or a little bigger with devices in a building, but mainly that's it. The network size is somehow limited by overall bandwidth, and there is no processing. So the system knows where to address the information, but that's it. There is no advanced addressing like IPs or whatever is part of layer 3 protocols that are tools we can use. Actually, if you are running a Dante network for your events, you are using these tools. And I learned that I was using these tools much after setting up my first Dante network. So how can I make this layer 2 more efficient? Reduce the amount of broadcast traffic, disconnecting hosts that are not transmitting or receiving. Or I can create inside, let's say, my building, smaller local area networks called virtual LANs or VLANs, working on a physical switch. So I can have my friends from UK built this amazing music venue. I have a front of house console with a stage box. I have a monitor console with another stage box, and I have lighting controls. This is my setup. This is my network. But obviously, I don't want the lighting control to interfere with my audio. And unluckily, I have a single switch. So what I do is to isolate the audio on a VLAN and having the light control on a different VLAN. Actually, what I'm doing is breaking into a switch, dividing it, and keeping the two VLANs separated, as if I had two switches. There is no communication between different VLANs. Obviously, before or while I think about the logical connection between different transmitters and receivers, there is also a physical topology to take care of. This was very common long time ago, and we see it with computers, but actually we may see it with a MADI stage box, mixer, and a processor. Every piece of cable is separated from the rest. It's cheap to install, can be slow, but as long as the project has been done for the audio, we don't care about it. It's as it is, so we just connect it and it works. And a single device failing doesn't affect all the other. This is what we call bus topology. Can we build a bus topology with, I don't know, our ULXD as well? They have two ports. I connect them in cascade, and this is classic bus topology. This one. Or I can have a little more safety with a topology called ring. This is, for who is familiar with optocore, this is the way optocore builds its network. Here it's shown with some BSS stuff, but you can imagine every device instead of it. So the signal can travel all over the ring, and if a single connection breaks, my network is still operating. Then we can have star topology, but everything is connected to the center of a star. That's the switch usually. So here I have 3 receivers. They have their RJ45 port connected directly to the switch. Now, that's having very good performances, but if my switch breaks up, my network goes down completely. So these are the things we should always consider when we build a system from scratch. I'm going very fast, but if you have questions, please stop me. But obviously, if you compare the ring topology, so having a ring connecting all the different devices, and this one, you can understand that here the switch can be the more delicate part, and in case if it fails, all the network goes down. Now, in the real world, we use hybrid topologies most of the time. First of all, because we often need several switches in a network. So we can have an example, ring topology mixed with the star topology. And if you think, this is thinking small. If you think big, internet is a bigger hybrid network we ever built. All the computers are interconnected in thousands of different ways. And it's kind of resilient because if my laptop fails, the internet is still there. If I disconnect a switch, internet is still there. So even if I disconnect thousands of switches together, the network is still operating. Now, without going too much in details, there are a couple of things that I will basically just mention. And the reason why I'm mentioning them is that these things can create problems to your installation. So even if we don't dig too much in details about these things, I'd like you at least to hear the names, to understand basically what are these things doing, what's happening in the background, because if something goes wrong, you have at least a couple of points to search and to understand exactly, to see if is exactly that thing going wrong and disturbing your network. One of them is spanning tree protocol. Now, what happens in a ring topology is that all the devices are happily communicating with each other up to a point where we have a loop. There are ways to avoid this loop. One of them is giving IP addresses. But let's just forget for a second all these things and just think about the pure information going all over the switches. If I have a kind of feedback, I need something to disconnect one of the parts of my ring to avoid what is called broadcast storm that will be seen and will be perceived by our network as an insane amount of data going on, even if we have few channels on air. So the spanning tree protocol is breaking the connections to prevent loops. But it's reducing our confidence in the network, because once that's active, it breaks our redundant concept of having a ring. So, blocking some ports, spanning tree protocol, or its advanced version that it's called a rapid spanning tree protocol, can prevent these loops, but what we lose is a level of redundancy. Here we have some example. It's more the STP, once the spanning tree protocol switches off or exclude from a loop one port, it takes up to 1 minute to recover and to reopen this communication. The rapid spanning tree is much faster, less than a second, but still it's much slower than having a primary and secondary Dante network. So this is why whenever you are building a Dante network, the recommendation coming from Odinate, not from me, but I'm not a trusted source of information about networks, is to avoid using rapid spanning tree protocol and to have two completely independent networks without rapid spanning tree. Now the question we saw before, but we can build okay. There is a break, they tell me from the directors there. So how long is the break? 1:05. Okay, I'll see you there, here in 15 minutes.
up on the hill. They think I'm okay, or so they say. Chinese music always sets me free. Angular banjos sound good to me. Asia, where could my time dancing is through? I run to you.
Yep. Okay. Shall we go? Any other question came to your mind about any topic that we can?
How does the clocking work between the microphone and the receiver? What signals do the clock?
Yeah. Any other question? You're shy, guys. You're not helping me. So before we go to the more interesting stuff, but I keep it for later to have your attention a little more. Let's talk about how can we communicate about different VLANs. So can we isolate part of the networks? But there is a way also to transfer relevant information from different subnetworks. So we have small parts of the networks called VLANs. In this case, it's super simplified. We just have two different VLANs. And for some reasons, we may need a device that lets the communication flows between the different virtual local area networks. This device is what we call router, and it's something a little more complicated than a switch, because it's using a different addressing system. Sorry, we are repeating things that are not. So, if in the layer 1 we used to have a hub that's purely a repeater, and in layer 2 we have a switch, but it's having many ports usually, and it's used to connect different pieces of networks, and eventually can be divided in small subnetworks. A router usually has less ports, so it's not used to do all the connections. It forwards data based on a different system. The addressing is no more MAC, but it's IP address. And it's smarter than a switch because it can learn the best way to connect different points of a network. So what we commonly use are layer 3 switches that have some understanding of basic routing protocols, so they somehow know what's going where, and they work on IP addresses, but they don't often have all the features that a router has. That's pretty much depending on the model and the kind of switch we use. Some features can be enabled, some features can be managed, some others cannot. Our switches usually are having smaller routing tables, so they can interconnect a lot of things, but not as many as the big networks like internet, and can have layer 3 protocols, and they can have features like quality of services, IGMP, and others that we will see shortly. So which layer works best for us? What is the best layer to use? It doesn't really matter. There is not a given answer. It depends a lot on the application. And layer 1, if you remember, I said try to think about a Russian doll. Layer 1 is always there. Anyway, there is a cable connecting my laptop to the rest of the network. The transport of a physical layer is always there. Layer 2 is the basic knowledge of what's transferred where is important. And the difference between layer 1 and 2 and layer 3 is the ability to interconnect different networks. Now, even if we have layer 3 capabilities, in example, Dante is a layer 3 protocol, we may want or we may need to treat it as a layer 2. If we are running a show, most of the time we don't have any other traffic, any other data on our networks. But if we are having a video conference facility in a building, most probably it will be sharing the infrastructure with other services. It's the two major protocols nowadays are AVB and Dante. So we quickly see some common points and some differences. AVB is an open standard, while Dante is proprietary. It's built and the chips are sold by Odinate. They invented this protocol and they are selling chips to different manufacturers so they can have Dante on board. AVB so far is a layer 2 protocol, so you can build a network, but you cannot share the network with something else. while Dante is a layer 3 protocol. This is meaning that that I can buy Cisco, any IHP, any brand you can imagine, the switch of any brand off the shelf and use for my network, while AVB requires certified devices. AVB is having a bandwidth reservation. So let's say that a complete amount of bandwidth, a certain part is always dedicated to a certain channel, etc. It's automatically managed. It's not that you have to tell the system how many megabit of bandwidth you want to reserve for each channel, an example. While Dante is not having this reservation. AVB, for several reasons, we're looking like the big new thing, but it's somehow not yet adopted by many manufacturers because they slow down a lot the process of certifying devices, and then they change the test to certify a device as AVB compliant, and it ended up that nowadays we have only really few products AVB fully compliant, while Dante is widely adopted, and many manufacturers decided to go on to use a protocol that was already there. Shure is one of them. And these two are protocols, and there is a standard on top of every layer 3 protocol, but it's called AES67. It's an open standard. The rules of AES67 are decided by Audio Engineering Society. And AES67 is allowing the interconnectivity between different layer 3 protocols, mainly Dante, QLAN, Ravenna. And most of the chips released in the Dante world by Audinate are now AES67 compatible, but not all the AES67 compatible products are really compatible if you try to connect them together. Anyway, we can see in the future AES67 to become a kind of common ground for whenever there is a need to connect different kinds of networks. What AES67 allows is to transport audio, to have a clocking, and to have a quality of service. We will see shortly what quality of service mean. But what AES67 doesn't do, and we probably won't do anytime soon, is the control part. So in the AES67 world, we will not be able to control the devices as much as we can do inside the Dante network or a Ravenna network. And it does not it doesn't automatically discover the devices in the network. While Dante does it, while Ravenna alone does it. So what are the things we need to know about? First of all, what is an IP address? I think we all use it. It's used as a logical destination or endpoint. So every device that needs to receive data has to inform the network about its address. And this is permitting the communication at a layer 3 level. Each device needs a unique IP address inside the network to avoid conflicts. And this one, I'd say, is the most common cause of problems in the small networks or medium networks that we build every day. If we have two devices that for any reason are having the same IP address, we will run into some kind of issues. And the devices that need to communicate, they have to be in the same subnet. Now, how a subnet is defined is part of the IP addressing knowledge that we will hopefully gain. You already saw it. These are the number of status that we have for the different number of bits. And, sorry. Okay, every part of the IP address is made by 8 bits. If we go back a little bit, 8 bits are 256 possible different status. So we have 4 octets or bytes building an IP address. That may look like this: 192.168.100.001. This is the easy way for us to remember it, because obviously the computers are not reading anything else than 0 and 1. So this is how an IP address looks like for a computer. Here there is some mathematics. If we combine all the possibilities, we have 4,294,000,000 blah, 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 blah possible devices. Definitely, it's enough for any audio system we build. We run out of budget much before running out of IP addresses. But it's not enough for all the devices on the planet. So to go over internet, there is also an IPv6 that I don't want to even mention, so a higher number of a more complicated IP addressing system. But what we notice, the first thing we notice is that IP address is not fixed, given per each device. It can be changed. This morning, the IP address of my laptop can be 192.168. Whatever, and tomorrow, or in few seconds, if I disconnect the cable, actually, can become 169.001. Whatever. So the IP addressing is not, as the MAC address, related to the device, but it can be changed. And we divide the IP addresses in three classes. If we don't have a direct access to internet, so if to reach internet, we go through a router that will be connected then in the big network, we mainly use private IP ranges or class C, but for our needs, usually 254 different IP addresses are more than enough. And this is why most of our IP addresses are falling under these categories. And this is why most of the IP addresses we deal with are beginning with 192.168. something. So, will the devices talk to each other according to the different addresses? Can we say it before even connecting cables or doing an actual test? Yes, we can understand it. We can think that the subnets that are different portions of a network and the devices to communicate, they need to be in the same subnet. So how can I define if two IP addresses are in the same subnet? Looking at the subnet mask. The subnet mask is made by 4 octet again, and it's telling me in this specific case that to communicate with my first IP address, if there is the number 255, I need to be exactly in the same range. So my IP address to communicate with that IP address has to be 192. And again, 168 and 1. And the last number is different. Now, if for any reason I want to build a bigger subnet, my subnet mask can change and can become 255.0.0. In this way, I will have 256 by 256 possibilities or different IP addresses. So this is a very stupid test. We have a first IP address, then we have a subnet mask, and then we have a list of IP addresses. And the first one is compliant with the rules dictated by the subnet mask, so it will communicate. While the second one will not, because the third octet is a 2. And our subnet mask is saying, no, I need a 1. To have this IP address communicate, to let it communicate with my main device, usually the first device is the switch in terms of IP addressing, I should change the subnet mask. I can bring it the third octet to 0, or in this specific case, even to 244. Then it will accept the 2 as a number in the third octet. The third IP address is working because, again, it's compliant and it's different. And here we have different examples. Some of them will talk and some other will not. How do I get an IP address? There are 2 ways. The first one is perhaps the more comfortable for us. We decide the IP addresses. So we set the devices in static. We manually assign the IP addresses. And this is a recommendation. We write down a list with all the IP addresses to avoid to have 2 devices in the same address. And then there are 2 ways of having an automatic addressing. The first one is the link local, and the second one is the DHCP. Now, if I connect my laptop to a single receiver without a switch in between and without a DHCP server, what happens is that they will, by default, have an IP address that is communicating. But it works only if I'm connecting my laptop directly to something else. If I need to assign multiple IP addresses, the best way is to have a DHCP server. That's acronyms for Dynamic Host Control Protocol. When I switch on the DHCP server in my switch, what happens is that the device I'm connecting is asking for an IP address, and the DHCP server is assigning different IP addresses for every and each device. If I don't have a DHCP server, or I switch off the DHCP server, the new device in the network will ask for an IP address. It will not get any answer, so it will be waiting for a while, and then it will fall somehow in a generic area that is 169.254.x.x. And the subnet mask will be more flexible, so 255.255.0.0. And this is called the link local mode, and allows automatic connection between devices, but it's not recommended when we are building the network. With subnet, we can decide how big we want our network to be. Obviously, we should try to keep it as small as possible, because it helps the infrastructure to be more efficient. If someone is a proper IT engineer now will feel that what I'm saying is a big simplification, but it helps. So here we have different values of a subnet mask, and here we have a number of possible hosts. Another thing that is worth mentioning is what we call IGMP. IGMP means Internet Group Management Protocol. It's a characteristic of layer 3 protocols, and it's used by hosts to form multicast group membership. Do we really need to know this stuff? Actually, no. The system will work even if we completely ignore what IGMP is. It will let us work as well. But it can be a tool that we use when we need to add efficiency to a network. Now, there are two ways to send out signal. There are many more, but we consider two ways. One is unicast. So in my Dante controller, I select point-to-point connections, and I put the stress. If I have, let's say, 10 devices connected to my Dante transmitter, or my wireless receiver that is acting in a Dante network as a transmitter, it can be connected, let's say, to 4 different devices. Now, if I connect it in unicast, it will send out the data 4 times, it will flood the switch, and then the switch will forward this data to any and each port. That is everything but efficient. Now, if we have a super powerful switch, a very robust network, and few channels, we don't care about it. But there are situations and conditions when we are obliged to use multicast. Multicast, what is doing, the transmitter is sending out the data once, and then the load goes into the switch. The switch is repeating the signal many times for every part. Now, some receivers, some ports will be relevant for our communications, so we want our flow to reach another device. But for some other devices, it's purely useless to have this amount of data. So to reduce the stress of a network, IGMP is helpful. In our situation, without IGMP, we have a transmitter that's sending a multicast information to every device on the network. And we have a lot of traffic that we don't really need. IGMP is based on subscriptions. So the switch is asking the devices, who is interested in receiving, let's call it this postcard, and we route the relevant traffic, the relevant information only to the devices subscribing the multicast group. So a device can join the group, and then the multicast traffic is only sent to members of a group. So whenever we have a lot of traffic in the network, and our switches are reaching the limit of their possibilities, IGMP snooping, IGMP can be helpful, can reduce the load. Now, if you go on the Odinate website, they recommend to use 1 gigabit switch. But it may happen that you only have a 100 megabit switch available because it's older, because you got an accent rack and you have an amazing and beautiful AXT620. That's 100 megabit. In that case, if you have sources that have to reach several different receivers, multicast is useful, and to reduce unnecessary traffic, activate IGMP. It's a simple switch inside the virtual switch inside the physical switch. You connect to it and you can activate or deactivate. The main reason why I'm mentioning this, even if a little bit running, is that can be extremely helpful for troubleshooting. Especially when you have devices that are appearing and disappearing from your network. IGMP snooping can be the reason why this is happening. Now we skip a little bit the rules about the subscription. Just bear in mind that it's something you may need to look when your network is not performing as you expect. So bandwidth versus speed. This again, can we operate a wireless microphone without knowing all this stuff? Yes, we do. But again, as the main focus of today is Accent Digital, and as it's having a Dante, actually it's having 2 or eventually 4 Dante ports, can be relevant to have some knowledge about what is around our wireless receiver and how to troubleshoot problems if they happen. So what is the speed of a network? Is the time that one data packet needs to travel from one point to another. While the bandwidth is the theoretical maximum number of bits a network can transport in 1 second. So the two things are related, but it's not exactly the same thing. So the bandwidth here is the road. Here the example. So what's making the difference is not the cable connecting the two switches, but it's how fast the switch is processing the information and transmitting them and moving them around. Obviously, when we are talking about audio packets, so we need to think that what's relevant for us is to have a less possible latency. If the switch is not quick enough processing the information, it can add latency to our system. Later on, we will see the Dante controller, and we will see how the difference between 100 megabit or 1 gigabit or more is represented and how it changes the values of the latency inside the Dante network. If I can find. No. Okay. Yep.
Before we go on, so you're saying it's not the cable in between the two ports that's making the speed fast. It's actually
The switch.
the switch itself. Because I did that once. I had a Cat5 cable in between two ports, but I changed it to a fiber, and it automatically just made it much more instant. I should say in that sense.
It changed to fiber.
2 gigabytes in between the two routers, and I had the two linked to each other, and it just made it instantly fast.
Actually, it sounds a little strange to me. Also because there is a converter
Yes.
that should add somehow latency, not reduce the latency. So I can't really tell you why, but it doesn't. So perhaps it was a specific condition of that specific network, because actually the cable itself shouldn't change, and if you add any conversion, you just add latency. Even if the conversion between an Ethernet cable and fiber is really super fast, in order of microseconds, but still it shouldn't help. Perhaps it was that kind of network was supposed to work on fiber and not on RJ45, or what kind of devices did you connect?
I used two Galileos, basically two processors on either side, because it was over 150 meters.
Okay, this is, sorry, okay. Okay, now I got it. The problem is not the cable, or better, is the cable in that case, because Ethernet cable are not working over 100 meters. The power then drops down, so to get this, obviously, yeah, in this case, it was much faster. But with Galileo, now perhaps the new ones are having also digital input and output, right? The last one I used was having only ASMU. That's it. But yeah, there is a limitation in the Ethernet cable. They cannot run more than 100 meters. If you want to do it, you have to put an active repeater in between to refresh the signal and make it stronger so it can travel for longer distances. Again, another somehow nerd thing. Usually, when we transmit data, let's say the controls of a Galileo or the Shure network. When we talk about controls, we communicate with TCP, that is Transmission Control Protocol. What TCP is doing is sending an information and asking the receiver, hey, did you get that information? Cool. Yeah. Now, this is very nice because you have a kind of control, but when it's about audio, it's totally useless because if you received or not, it's already too late for me to do anything. So, to reduce the traffic on a network, the protocol we actually use for audio, it's called UDP, User Datagram Protocol. So when we have different DSP systems, we can have obviously different levels of latency. And the latency somehow can become a little bit unpredictable. Even if it's few milliseconds of latency under certain conditions can be relevant. If I have 2 milliseconds of latency while I'm aligning a PA, it can be an issue. So, how do we fix it? We need a precision clocking that keeps all our network with the same timing and at the same level of latency. This one was one of the major reasons of the success of Dante networks in the industry, because we can decide what's the amount of latency at the different points. What's happening is that we have priorities. The first information that has to travel is obviously the clocking information. And then there are all the packets related to the pure audio, and then all the packets of information related to control that can travel a little more slowly than other packets. And not only that, if we are pushing a Dante network towards the limit, and we can see some red dots when we will see the stress of a network. Here, the network is too small to really demonstrate it because we don't have enough transmitters and receiver connected. But when the networks start growing, we can really see it. Another feature that Dante has is to decide that, let's assume a show, all the channels that are feeding the front of house console, they need to work with a minimum latency, while the feed that's going to my multi-track recorder, if it has 5 milliseconds of latency, as long as it's consistent, I'm perfectly fine with it, right? This is another feature that Dante has. So let's say I don't have a gigabit switch, or even with a gigabit switch, I have many, many channels and many different feeds, front of house, monitor, and then 4 feeds for broadcast, easily. They don't have to be at the same level of latency. And this is another reason why Dante can be extremely efficient. As we said, networks are moving bits, 1 and 0. Some of them are more critical than others. So audio is important and is much more related to time than our pictures or our emails or our Facebook posts. If I post something on Facebook and I have 2 seconds of latency, who cares? If my kick drum has 2 seconds of latency compared to the base, that's not that good. So how do we have a reliable, and how do we organize the network in order to have a more critical data sent over faster than the data I don't care about? It's called quality of service. And this is the way the networks are using to understand if a traffic is critical, time critical, or if it's not. So real-time audio traffic over UDP, User Datagram Protocol, is more time sensitive than, in example, the PTP. And all these things can be managed in a page in our switches that is called quality of services. So I can have different priorities. Here the example is made with a QLAN network. The Q4 has the highest priority, is the clock, and the same is for Dante. The clock obviously is what keeps our network together and is the first information we want to send. The audio streams is what we are transmitting, and obviously it's more important than the VoIP, so voice over internet protocol, or the video, even in a conference call. And the lowest priority is given to all the other data. Now again, if we build a system for a show, usually we don't have to deal with it because we don't, the quality of services that is set up by default is already enough. But under certain conditions, we may need or we may want to be able to change this priority for whatever reasons. So it's a good thing to know that they are there and we can work on it. Network cables. Always check your cables, yeah, because as the common thing between analog and digital is that we can really spoil an installation, millions of dollars, just with the bad cabling. There are some differences between Cat5, Cat5e, and Cat6. But usually we work with the Cat5e cables at least, or Cat6, or better. Crosstalk is not relevant for what we are doing. So if we don't do laboratory immersation, we don't care about it. And very important, the maximum length is 100 meters. So 150 meters for a network cable is too much. Doesn't matter if it's Cat5, Cat6, Cat23, 100 meters is the limit. These are having actually 8 cables inside, 8 core cables. They can be shielded. Cat5e versus Cat6, if our network is 1 gigabit, doesn't make any difference. Again, shortly before we finally move into our new boy, few hints about Dante and how we can connect it. So the main way, or let's say the most common way is the switched mode. In this case, we have 2 Dante ports that are labeled primary or secondary, but in switched mode, they are sending and receiving exactly the same thing. and the audio and the control is sent over both ports in the same way. Then there is the redundant audio mode. We have two different VLANs inside our device and possibly two different physical networks. On the primary, we will have the audio and the control. So all these services like automatic discovery of different devices. And on the secondary network, we will only have the audio. This is the reason why if I lose the primary network, I'm not able to change the routing of the device, but the audio is still flowing. While if I break only the secondary network, I may not even notice it. And then there is a split mode. We have two different VLANs. On one, we send the audio, and on another one, we send the control. Now, I hope you don't mind. We skip a few slides. So what are the takeaways of this small section? Networking is here to stay. We will have to deal more and more with these technologies, even if we are audio engineers. It's here to stay, even if it will not completely replace the analog connections. Most probably our world will remain hybrid for quite a long time. I remember the first time I had to do with a digital network. We were having two big analog Soundcraft 5 boards, and for some reasons, I think the distributor was very close to the rental company I was working with. We got an optocore system. So what we did is to bring active splitter, then connect the monitor console with directly to the active splitter, and the other feed from the splitter was going into the optocore stage box. We were running two fibers, reaching another breakout box at the front of house. If I think about it now, it's kind of ridiculous, because we were using a digital transportation, adding latency just for nothing, because we didn't have any digital console. Somehow, I think the way we are doing the things now, in 20 years, will look the same. We still have a lot of conversions. We still probably convert the audio at least 3-4 times during the full path, and the direction is more and more to integrate a single conversion point, being in a digital world for whatever is related to transport and processing, and then having a conversion just before the speakers or the output that we need to have in ear monitors, whatever. Layer 3 versus layer 2, what we need to remember is that layer 3 is more agile. We can do more things. It's not always needed. Nevertheless, we can use a layer 3 protocol. That means a layer that can share infrastructure with other information, that's able to prioritize the audio versus everything else in a closed network such as a layer 2 network. So we don't really have internet traffic between our stage box and our console, but it still remains a layer 3 network. networking is easy, and if we can do it, then everybody can. If I was able to learn, absolutely everybody can. What we need to think is that as audio engineers, we have been trained to think about the signal path, like the different stages. Here it's not really different. Once we have clear from a logical perspective and not only from a cabling perspective, which signal is going where and what are the points that needed to be touched before it reaches its destination, and we think logically, it's quite easy to troubleshoot a network issue in the real world. And it's just 1 and 0. So at the end, for our network, audio and emails are not making any difference. We are using IT technology. So we just sometimes need to think a little more as computers than human. So I hope this part was not too boring. If it was, I'm sorry. No, I'm not really sorry. Yeah.
We are on a single network only. What traffics can we expect if we're not sharing networks with anyone else?
It depends
On the devices or
on the amount of channels, on the bit rate and the sampling rate of your audio channels, and how many channels you really have on air.
that's all traffic.
Yes. We said that roughly 24-bit, 48 kilohertz, single channel is slightly more than 1 megabit per second. Think that a switch not really perfect for Dante is having 100 megabit, and Dante, the Audinate is recommending 1 gigabit switch. So you should have,
So that can be another traffic.
yeah. By the way, we can do it. Anyway, you can control the traffic on your Dante network at least. Here. Now we only have 3 devices. None of them is doing anything, so not really much traffic here. There is no routing happening, and I only have 1 receiver that can accept 1 channel per time, so it's not really easy to demonstrate. But here, when you have a network status, you can check how much traffic you have for every port, for every device, and if everything is working properly, or if there is an issue, it will be displayed here and here. Are you familiar with the Dante controller? So perhaps it's nice to spend few words, really few words on it. The Dante controller is a free software. The only thing that Audinate is giving away for free. Everything else has to be paid. And not even a cheap price sometimes. And it's our routing device, our routing app. We can decide what goes where. Automatic discovering, so I have AD4Q, that's my Axon Digital receiver. Here, even if it's a receiver, it's considered as a transmitter. And I have 2 ULXD, a dual and a quad. Now, if I add more receivers, it would be more nice. Here, the only Dante receiver that I have is AD4Q. So the X in digital, that's not only a transmitter in Dante world, can be a receiver as well. And I can decide to connect, in example, the output of a ULXD to the input of this X in digital. Here, if I add, I can probably activate here. I activated Dante Virtual Sound Card. That is one of the very nice thing that Odinate charge for. And now my computer is a Dante device. So I can have 16 input and 16 output. I can set up my sound card up to 64 by 64 actually, using Asia drivers. Anyway, and here in the Dante network, I can purely route my signals, and I click in the intersection, and I have in the first 2 channel ULXD, then I have other 4 channels of ULXD, and then last but not least, now, in this network, I clearly don't need any multicast feature because I don't have enough transmitters and receiver to need it. Anyway, it can be useful to see how different devices look like. I have 1 receiving channel. Now I'm connected to the X in digital. I have 4 transmitting channel. I can check the status, and here I have an interface telling me the IP address, the MAC address, how many transmitter, how much the transmitter part is using, how many errors do I have. I can set up the latency. Yeah, obviously, if I connect it to something. Then I can do a basic configuration of a device. So I can rename the device, in example, in a more human way. So it's called XND instead of a weird name it was having. I can decide the sample rate. I don't have any possible encoding configuration, and I can set up the latency. So if I have up to 10 switches in a gigabit network, or I have a gigabit network with 100 megabit per second switch somewhere, the recommended latency is 1 millisecond. I could try to push it down to 500 microsecond, but might not work. And if I have more traffic in the net, on the switch, I definitely need to follow what Dante is suggesting me. And then I can decide how do I want to configure my Dante switches, and if I want it to be on DHCP or in manual mode. I can identify my device, and I can create a multicast flow. I can decide to create a multicast flow for all my channels. And I will see it here. So in case I need to send my Dante channels to more devices, I will not have a lot of traffic from the wireless receiver to the switch. The switch will take care of splitting the signal to different receivers. We will see a little more on this device. Now, director, when is the next break for lunch? Directors, when do we have the next break for lunch? In 30 minutes. Okay. So when the engineers were asked to produce a new wireless system, they saw of what was already available, what were the products with a certain amount of success in Shure history, and they saw that reliability was the main characteristic of UHFR. I think that independently by emotional things, or if you have to run a show and you have a bunch of UHFR, you feel somehow comfortable. You may prefer a different name, brand, model, different capsule, but you know that the wireless microphones will not be a big issue in your show. Most probably you will be quite happy. On top of it, a few years ago in 2012, Shure introduced a bunch of new technologies with the Accent Wireless Manager system. So it was not only a transmitter and a receiver, was a full ecosystem having certain characteristics and a very advanced level of technology with remote control, interference detection and avoidance. So a good amount of features that were really useful. And on another note, with the launch of ULXT, we saw the spectral efficiency, so the number of channels per TV channel, the number of wireless microphones we could have in 8 megahertz increasing dramatically. And every and each of these systems was having a limit somewhere. Sorry, Yes. So what they came out with is Accent Digital. That's a system built from the ground up. It's not that they had the circuitry of UHFR and the digital modulation of ULXD, some accent features here and there, a new packaging, a new sticker, yeah, here we are. It's a product that has been built and designed from scratch. So the modulation scheme is completely different and much more advanced compared to ULXD. There are features that we will see them that are increasing the reliability and the resilience of a system a lot. And they also improved certain weak points compared to ULXD. Example, the diversity. We don't have predictive diversity anymore. We have a true digital diversity. It's much more than a sprinkle of accent features on top of ULXD. And we will see when we will start connecting the system with Wireless Workbench how it's changed Wireless Workbench and how many new features have been already introduced thinking about accent digital. And it's definitely much more advanced than UHFR. The project has happened like 10 plus years later, so a lot of improvements since that kind of technology has happened in the industry, and accent digital is reflecting these changes. A little bit of marketing. Sorry for that. But I was mentioning the spectrum in the United States as much worse of what we have here. And actually, it really is. I have a few pictures of a scan inside the Las Vegas Convention Center. It's crazy, really, really crazy. Something we don't have here yet. But the spectrum is still shrinking, and the number of users is growing. So we cannot expect, from a regulatory perspective, an improvement. It's just a matter of time, and even here in our nice place, we will have the same spectrum they have in US probably, if not worse. As we got the VAT, we will get also RF pollution. But to ask someone to invest money in a wireless system, we need obviously to have a perfect audio. We need it to be very stable from an RF point of view, and we need more than before spectral efficiency. And actually, this is somehow what's happened. Differently than ever before, we will have a common platform based on a receiver that will support two different families of transmitters. Today, we only have one of the two families here. I did my best to steal at least one transmitter of a second family, but it's not yet ready. I mean, it's ready, it's there, but I couldn't get it. Maybe some of you saw already also the ADX family. That is the family with show link control enabled and some other things that we will see. While the AD series, the AD family, the one that we have here today, is what it's called the UHFR replacement. So it's having all the benefit of the new RF design, all the benefit, all the different characteristics given by this kind of receiver and this kind of RF link, but it's not having remote control. This one is both the families have been launched. The AD family will be available starting in July, while the ADX will start to be available early 2018. So perhaps you will start to deal with it. I think most of you are technicians, right? There is not any general manager here or owner of any company. So most probably you will see them appearing next year. Anyone is the owner? No. So, to talk about Accent Digital, our fantastic marketing department, build this slide to condense a little bit the thousands of things that, from a technical perspective, I would like to say in 4 major points. High RF performances, and this is really definitely the more stable RF system that Shure ever did. Obviously, I don't really know about the competition because I didn't have the time to do testing, but definitely is much more robust in terms of RF than anything else we did before. And it has the capability to manage even the worst dramatic kind of spectrum we can have, that is a crowded spectrum where we don't have much space and we have a lot of noise floor, and we will see how this high RF performance can be also monitored in a different way than before. When we talk about a high-tier system, we don't even think about audio quality. It has to be there, period. We don't even consider a microphone that doesn't sound really, really close to the wired equivalent. It's not even a point in discussion to have a system that sounds, yeah. Command and control, we saw that wireless workbench is kind of popular and helpful. It's not just still there, obviously, but we improved wireless workbench to accommodate all the features of Accent Digital. And we will see we will talk a lot about it, but we will see there are really some tools, small tools, really made for engineers. I mean, there are things that will never be a selling point, will never be marketing, will never be, but are really useful once we know they are there to control the performances of our system. And hardware and scalability. It's a flexible solution and it can be scaled. But from our perspective, as most probably nobody in the room cares too much about the investment, the good part is that whatever we have been learning with the older Shure products is somehow still there, and there are just new features to add on top of what we are used to have. So the workflow is not changing dramatically, is not completely different. The structures of a menu is pretty consistent, but we just have many more things and many more options. So as you can see, the back panel is kind of crowded. Starting from the left, we have a AC plug, quite common. And we have also an AC outlet that can be modified and can become a DC input. This is not an everyday requirement. Most of the time, our wireless microphones can work with a single power input. They are in a rack, and the cabling, if the cabling is done properly, it's fine. For some application, we saw that the possibility to have a redundant power is helpful. So there is this option. And then we have a small Ethernet switch with 4 ports. 4 ports, why? We saw that many people don't really like to have in the same network the audio and the control. especially when it comes to big shows where the network starts to be an important part. Sometimes there is a dedicated network engineer. So these 4 ports can work in different ways. One is a pure split mode. So I have 2 ports for Dante and 2 ports for control. Or I can have a switched mode where every port is doing everything. So according to my needs, I can use these ports in different ways. Then I have 2 BNC connectors for clock. Please do not connect the antennas there. And then we have a 4 friendly and beloved XLRs. But 4 of them, they obviously can send out analog audio. But 2 of them, the number 3 and the number 4, can be repurposed and send out AES free signal. Obviously, 1 connector, 2 channels. We have a switch between microphone line, ground lift. That's pretty common. Then we have a TRS jack output that is always available. Doesn't matter what's the purpose of XLR connectors. This is meaning that out of this receiver, we can have 4 different flows of audio. Dante primary, Dante secondary, then we can have XLR sending out digital audio, AES free. In case you have AES free and Dante working together, a word clock connection is highly recommended. And the analog output going out from the TRS connector. And then we have 4 ports. Again, I think you saw it in the back of every high-tier Shure receiver. AB, antenna A, antenna B, 2 input. But here, the other 2 are called C and D. By default, they work as a cascade output. So it's just a passive splitter sending out the same signal that's receiving. But they can be 2 additional inputs as well. That's something I'd say new. No, actually, no, it's not I'd say, it's new. And it's a unique feature of this system. You can have 4 antennas connected at the same time instead of 2. And this mode is called quadversity. That's the receiver will come in a dual. You will have a dual receiver or a quad receiver. The quadversity can be activated only on the quad receiver. What happens with the quadversity mode? We have these two RF channels working together and being combined. So instead of a traditional diversity, we can have 4 points to pick up the signal and to get the best RF performance. This can be used in several ways. The first one is to extend the coverage area. So we have 2 antennas on stage, and let's say there is a ramp or a catwalk where the singer goes 30, 40 meters away from the stage. We may need to place a second pair of antennas, or we want to have a second pair of antennas in the green room because he or she wants to start singing from a green room, or another kind of situation, we can have a red carpet or whatever, a parade. So we can put the two couples of antennas apart, or we can use these 4 points to collect data in a very crowded and noisy environment, even close to each other. Now, today, I connected the Quadversity system. A and B are the antenna you can see next to the screen, the one with the omnidirectional and the directional together. That's called the diversity fin, I think. So this one. And then I have the two Shure antennas at the side of the screen. Here, it's not a big deal. If my microphone drops out, it's not the end of the world. We don't even have an LED screen producing interferences. But there are some applications where Quadversity can make the difference. So what we lose to get these 4 points is that the quad receiver becomes a dual receiver. So channel 1 and 2 will actually become channel 1. The 4 independent RF lines are merged and combined together, and this is different of having a passive splitter. Passive splitter is just summing what's coming from the 2 antennas. Here, the system is actively looking into what's coming in and deciding how many data are relevant. We have a new modulation scheme. Will not go too much in details into it because the engineers didn't go in details with me. Even during the training, there was like, you can't understand, and they were actually right. I couldn't understand. When they started explaining, I was a little lost. But as we said, it's a kind of QOM modulation using a mix of phase shift keying and amplitude shift keying, allocating the different layer of data, but it works very well. This is something we can measure, and the room is not that big actually, but we can compare eventually, even going out, different microphones to see what the performances are. And this new modulation scheme is actually carrying many more data, many more information than the old one, the one we use for ULXT in example. So what they did is to use this data to have more robustness and more control. They are, together with the audio flow, the transmitter is sending out a pattern of bits called pilot bits, and according to how many of these bits are correctly received, we can now have a channel quality metering. What channel quality metering is, it's before we had the quantity meter. How much RF energy am I actually getting into my receiver? Now, but if I put my receiver on top of an active interference, an active source of RF, the system cannot discriminate if it's something we need or it's just energy that we don't want. With the digital transmission and these new modulation schemes and these pilot bits, we can actually discriminate if a signal we receive is the signal we are transmitting, is good signal, or is just garbage we don't want to deal with. And we have a new high density mode. If you are familiar with ULXD, you may know that ULXD was already having a very efficient high density mode. You drop down the power of a transmitter to 1 milliwatt, and you could have a lot of channels on air. But in that case, we were losing coverage area. They redesigned the high density mode for XN Digital. Now the power output is, again, it's just a nominal number, but it's 2 milliwatt. But 2 milliwatt with this modulation scheme and this architecture has the same performances that we used to have with UHFR at 10 milliwatt. Meaning, in a good environment, 80 meters of coverage area from the antenna. That's usually enough for the majority of the shows. But we can have these performances with around 60 channels per 60 active channels, active transmitters per TV channel, so every 8 megahertz. So when we talk about audio quality, the first quality audio needs to have is no dropout. So the first thing is resilience and reliability. And we will see that somehow it's there and we can trust. But we need, obviously, we can trust the system, but we need, obviously, audio to be good, possibly better than before. And when we started speaking about the differences between digital and analog, here we don't have that much processing than we had before, so much processing as we had before. So the audio is captured by the capsule and immediately converted. It's converted, and what we send out is 24-bit, 48 kilohertz digital audio. So no limitations in terms of frequency response, no limitations in terms of dynamic range. The dynamic range of a 24-bit signal is about 120 dB, and the frequency response is really 20 hertz, 24 kilohertz. We have a lot of options in terms of audio output. We have a Dante output, we have AS3, we have analog, and in any case, latency is below 2 milliseconds. This is another big step. 1 millisecond may not look that much, but it's amazing how many things the engineers can make this machine do in 1 millisecond. Before, because of a different modulation scheme, there was the need for more buffering to have a reliable sound. Now, this buffering is much reduced than before, is more reduced than before, and whatever is happening much faster. And then we have encryption. The signal can be encrypted with AES-256. That's super reliable. It will take forever to break this encryption, even for the fastest computers. And again, it's there, it's available. It's maybe completely useless if we do rock shows or music shows, may become useful whenever we have a certain kind of customer. Command and control, as I said, it's working in the same ecosystem we had before. So wireless workbench and also the mobile app are still there, can still be used with Accent Digital. Actually, I don't have a version of Channels app that works with Accent Digital. It will be available in the App Store, I think July. But I have a wireless workbench version that's working with Accent Digital. So in the afternoon, we will see how wireless workbench changed to accommodate the new system. And for who is familiar with the Accent analog world, the Spectrum Manager, it's still there, it's still the same. There is not any plan to change it. It just requires a firmware update, and it will continue doing the same thing. That mainly is wideband scanning together with the possibility to deploy compatible frequency lists, compatible between themselves and compatible with the actual conditions of the RF spectrum. Dante browse, and I don't want to spoil all the surprises, but as you saw before in the Dante controller, differently than ULXD, Accent Digital is not just a Dante transmitter, so it's not only having an output, it's having also an input. And it has several uses. One of them, it's easy to demonstrate, and I will. Another one is by far more complicated because it would require multiple receivers, but we will talk about it. And network charging. This is very important in the last years. I'd say not only for Shure, but for many manufacturers. In my career, I changed perhaps 20,000 batteries. I don't know. I never actually made a proper calculation. I should. But fly cases of batteries. And I've been throwing away them. And there was no other real option. Before 2012, the rechargeable batteries, the commercial rechargeable batteries, were having an output, power output that was not enough to operate with wireless microphones most of the time. Or their discharging curve was too fast, the discharging was too fast to be somehow predictable. So what's happened recently is that Shure started building rechargeable batteries, ion lithium, so the same technology we use for our mobiles. And they put a chip inside the batteries that lets us know how much time do we need before the battery is fully charged or fully discharged. What are the characteristics of the batteries? How many life cycles? What's the health of a battery? And all these informations can be collected and analyzed by the actual charger that is part of a network. We will see it even if we don't have one of the new network chargers, but we will see how it is with the old Accent, and we will see a little bit the differences. Then hardware and scalability, that for what is our concern is like, it's important to know that everything is happening, is built inside the existing ecosystem. So there are new things to learn, but our workflow can still be consistent. From an inventory perspective, we will have a common receiver with two different kinds of transmitters that can be mixed and matched in any possible way. I will tell you some examples. And as we said in the beginning, we have a wide tuning range for the transmitters and the receiver at the same time. Now here, on the left of the screen, you will see the receiver that will be the first choice in Middle East. Receiver type A is, it can be tuned from 470 to 636 megahertz. So it's over 160 megahertz of tuning range. In high density mode, it means that we can have 1,200 active channels at the same time. So it's quite a lot. Yeah. Yeah. Sorry? It works, yeah. Actually, as they didn't have 1,200 microphones, they did the test only with the naked RF parts, because there was no way to. They didn't produce yet 1,200 microphones, but it's. You just have to multiply what you can do on 8 megahertz, and you can test it in your warehouse even if you don't have 1,200 microphones. And there will be another option if, for whatever reason, you need to operate in a different band, that is the 600 band. There will be a B receiver available. The frequency for the B receiver of the transmitters will be K55. That will be more limited. But that limitation is just a software limitation to be compliant with the regulations in UAE. You can have a device receiving on whatever frequency you like, but you cannot have a transmitter that's transmitting in not allowed frequencies. So this is the reason why there will be a software limitation, but it can be removed. Let's say that you travel, you are touring, and you go to do a show in Lebanon, where the 700 megahertz are available, you want to use them, you can. You just modify the frequency band in use with all the compatibility group and whatsoever, and you will be allowed to use also the 700 megahertz or more. Okay, it's time to have lunch. So 1 hour break. See you here 2:05. Prepare your questions, please. Huh?
So if I say I take the RXC, and I'm touring, so I want to use maybe 600, and then if I'm in Europe, and then maybe.
Okay, welcome back. Are you sleepy? Okay. You have to resist, I think, 1 more hour, and we are done. I'm still waiting for your questions anyway. So, I was so clear that you understood everything, or I was so confused that you didn't understand anything. Yeah. So before we start using it, a little explanation about what's missing today. As I mentioned before, Exim Digital will be a platform with a common receiver and 2 different transmitters. 2 different families of transmitters, actually. One will be the AD family with a body pack and a handheld that we have here. Even if the shape is similar to ULXD, inside it's completely another story. So different modulation scheme. What you have to think is that even if the 2 families are having some major differences, first of all, the form factor, the aesthetic, the batteries, and the show link capability, everything else is common. So all the good things I mentioned today so far are common to AD and ADX family. There is no big gap. The quality is the same. The RF circuit is the same. The audio is the same. Most of the options in terms of redundancy are coming out from the receiver. So it doesn't really, there is not such a big difference between the two families except the show-link control capabilities. So we have these two guys, and we will see what they can do, how we can use them a little bit. And then the missing part of a family are the ADX transmitters. For who is familiar with Axient, that show link is always there, just with a couple of modifications. Actually, you can see the old show link in its amazing shape over there, and the new one just in the pictures. The new one is having 2 antennas instead of 1. So, do you know what is show link? Okay. For who doesn't know what show link is, that's a 2.4 gigahertz access point. It's working in the same range of frequencies than Wi-Fi, but it's using a different language, that's called a different protocol, that's called Zigbee, to remotely control the transmitters, the Axient transmitters. This is including the frequency, the tuning frequency, all the audio aspects that are inside the transmitter. And the major thing is the ability to move the transmitter and the receiver to a new frequency whenever an interference happens. Or even, let's say, I'm doing my show today, I pack my things, switch off everything, remove batteries, whatever. Tomorrow I set up on a new show, I deploy my new frequencies, and if my transmitters are show link enabled, as soon as I switch them on, they will have a special connection with the receiver, and they will retune on a new frequency without any sync. While if we don't have show link, we have to resync it whenever we change the frequency at the receiver. Then we have the ADX1 body pack. Compared to the Axient analog system, the major difference is the battery. That's completely inside and enclosed this time. We saw that the idea of having an external battery was pretty cool for some things, but it was lacking in some cases a little bit of humidity inside the pack, creating eventually some issues under extreme conditions, in example under a heavy rain or on actors that were sweating a lot. So to be more waterproof, they placed the batteries inside. This family is working with special batteries. So they have their dedicated batteries. While the AD family is working on the SB900, that's the same battery in use for PSM or for ULXD. The body pack, the big one, is having 2 options in terms of connections. It can have a TA4F, the standard Shure connection, or a Limo 3. It's having an IP rate of 3, I think. That means it can be under a shower for 30 minutes. And I think they are submitting it. They are trying to find out if it can get the IP rate of 7. That's meaning it can work, it can survive after 30 minutes under 1 meter of water. So it's really, really, really much more waterproof than whatever we did before. And it's having 3 antennas. One is the UHF transmitting antenna, plus it's having 2 antenna here, here, and on the other side for 2.4 gigahertz communication with the show link. The handled, compared to this one, is more thin. It's a smaller handled, wireless handled Shure ever did. And they could make it a little smaller, but then it wasn't compatible anymore with the mic clips, so they decided to keep it the given dimension. It's having 2 antennas for show link communication, so it doesn't matter how the talent is holding the microphone, there is always one of the two. There should be always one of the 2 antennas available with a free line of sight together with the show link. And about the show link connectivity, one thing to mention is that we saw that with these microphones, the range was much more extended than before, even than accent analog. So to have the same, what you don't want once you have your show link control is to lose it whenever it reaches the edge of a coverage area. Because obviously, when it's more far, there is less RF reaching the antennas, and that's exactly the point where your system is more sensitive to interferences. So to match the UHF coverage, they increased the power of a 2.4 gigahertz. So the new show link is having two antennas in the show link and 2 antennas into the transmitters to match the coverage of the UHF signal. And then the last is the super cool and sexy ADX1M micro body pack. This is a very small body pack, and as you may notice, there is no connection for the antenna because it has no external antennas. But it's having 4 antennas inside. Having an internal antenna for UHF means that if we make a comparison holding the 2 body packs like this, the one with the dipole antenna, that's this antenna, is performing better. But usually, nobody goes around with the body pack like that. Now, what happens when I put the antenna close to my body? There is obviously the body absorption, so my body is absorbing a part of energy. But more relevant, this antenna is detuned a little bit. So its tuning is not perfect anymore. There is a small deviation from a precise tuning. And this is something it cannot be controlled on this kind of antenna. So the micro body pack is having 4 antennas. 2 are for show link control. 1 is an internal helical antenna for UHF transmission. And then there is a 4th antenna that is a sensitive antenna. This 4th antenna is checking what the UHF antenna is doing. So if everything is good and the tuning is still perfect, cool. But every few milliseconds, it's verifying that the transmitting antenna is performing at its best. And if not, if it sees a small detuning, it can electronically correct the tuning of the antenna, bringing it back to the maximum efficiency. This is why, even if compared on free field, the dipole is having better performances, when they are on a person in a real life application, the micro body pack is performing equal, so if not better, than a dipole antenna. Another characteristic of this micro body pack is the material. Having an internal antenna, a metal chassis was not really an option because it would have absorbed 90% of the RF energy. So they started investigating in possible materials, and they found out this special type of plastic that has several interesting characteristics for us. One of them, the first, is that it's completely RF transparent, and the second one is that it's not sensitive to the temperature. So if you bring it out of your drawer that was traveling by night in a very cold environment, it's not freezing cold. It's acceptable on the skin, so probably the talent will not complain, yeah, it's too cold. And after as it's very good in dissipating heat, even after 2-3 hours of continuous work, it doesn't get hot. It remains acceptable. So again, the talent is not complaining that before it was freezing and at the end of the show he has a nice red dot on the skin because of the heat. And another thing, another characteristic is that people, product managers have been speaking with several technicians, A2 and operators, especially in the theater and the broadcast environment. And one of the questions was, what doesn't work in the existing body packs you have available? And one thing that everybody noticed was like, every body pack is squared, but actually there is not any part in the human body that is perfectly squared. So the traditional kind of shape is not helping whenever there is a need to hide the body pack itself. So this rounded ergonomic shape is pretty good to hide your transmitter away. And obviously not having an antenna, again, it's very comfortable because often the antennas get raped just to fix it, hide it. So in this way, we get better performances and no compromise. This is the ADX part. There are TOC switches option. The TOC switch is an accessory that can be an accessory for the handheld. It's adding a special tone to the signal we send out. And this special tone is received by the receiver. And according to the settings, we can have like toggle to mute. So whenever the talent is pressing it, its mute microphone is muted for whatever reason. Or toggle to talk, so you press it and you are on air. Or it can route the signal onto different outputs. Let's say if I don't press, it goes out from the XLR and Dante, and if I press, goes out only from the TRS output. This can be useful whenever the talent want to speak, let's say, in the intercom, but not on air, or these kind of situations. Or in a musical in a concert, it can be useful to route the vocals, let's say, to a pedal board or this kind of things. While the ADX1 will have a switch separated from with the accent analog, the TOC switch is the on-off button, can be repurposed and be used as a TOC switch. With the accent digital, there will be an external device that will work together with the Zigbee in the 2.4 range and will inform the receiver that it has to change the routing or mute the microphone or whatever the setting is. For who's familiar with accent, this is a known thing. With accent analog, one of the major benefits was the ability to spot an interference, detect an interference, so understand that the signal received was not healthy, good signal, but for whatever reason, something else, and have a reaction to this situation. So whenever an interference happened, accent analog was telling us, what shall I do? Or you can set up your system in a way that asks you if you want to change the frequency, or it can automatically swap to another frequency. Recognizing an interference into the analog domain was kind of difficult because there was also a statistic, there was just probabilities that this is an actual interference and not something added for whatever reason to the audio signal, or because it was reading how much noise was in the audio signal. Moving to a digital domain, detecting an interference, it's much faster and much more deterministic, because there is, as I mentioned before, a pattern of pilot bits sent out from the transmitter and recognized from the receiver. Now, what microphone I have? A KSM-9. Perhaps if I switch on. I want to put the just give me a second. I'm trying to put the screen of a okay, 124. Dot 168.1.24. Okay. So in this way, you can see the screen. A little better. Okay. Now, if I switch on this transmitter, but I tuned it manually instead of syncing it, what we can see here is that it recognized an unregistered transmitter. And if you think about it, this is a perfectly legitimate Axion digital transmitter, but it's not one of the transmitters in the list of a receiver. So here is one of the decisions we have to take about our system. How do we want it to work? By default, whenever an unregistered transmitter shows up, the receiver will let the audio go through. So I will have audio at the output, but I can set in my preferences also the audio to be muted and the unregistered transmitter to be treated as an interference. Two small examples for it. I have 3 backing vocals but just one spare microphone. And the technician handling the backing vocals is on the other side of the stage. So in case we need be, he can be called, informed that something is wrong with one of the microphones, and he can quickly retune the spare unit and hand it over to the interested backing vocals. In this case, we want an unregistered transmitter to be able to pass the audio. Okay, we know it. It will appear on our wireless workbench and on our screen, but at the end, it will be treated as a good transmitter. But if we think of being in a festival, hopefully this system is going to be quite popular, and we may have several acts. Then, in this case, we may prefer to treat the unregistered transmitter as an interference, and if we have ADX transmitters on air, the system will move the frequency of the transmitter and the receiver on air to a new one. If we have AD transmitters, we will just get an advice, but the system obviously cannot move. It could move the receiver, but then the transmitter will be out of tuning. This is happening because of a pattern of bits that we are sending. Now, you asked in the beginning if we are now able to have two transmitters on the same receiver. If you mean switching on two transmitters and sending signal to a single output, no. The answer is no. We need always one carrier for each signal. What we can do is to put more than one transmitter in the list. And then, if we switch them on one per time, we can have several transmitters on the same receiver, all of them registered and all of them legitimate to operate.
So you can't actually encode the signal. So you can't actually receive like 4 different microphones on the same channel. So the way over Dante, your digital signal will be carrying a lot of channels. You can't actually encode more than one channel on the one channel carrier frequency.
Exactly. Whenever we switch on two transmitters on the same carrier, on the same frequency, whatever we get is just...
You can't clock that in such a way?
No. First of all...
Why surely you should be able to have the bandwidth to be able to... Would you not have the bandwidth to be able to add more? If they're transmitting digitally on the same carrier, would you not clock them so they...
No. For several reasons. First of all, the amount of data received is enough for one microphone and not for two. Second, what would be the use of this thing?
Well, you could use one frequency, because all the bandwidth's being used up, you could use one frequency and have several microphones coming down it.
Yeah, but then you wouldn't be able to control these microphones. If you are using them all together, you don't have any control. It's a single audio channel.
No, I have 4 different outputs, not... I don't think
Yeah, exactly. You get a quad receiver, you can have 4 inputs, 4 outputs. But you need 4 different frequencies. You can't work on a single frequency.
I'll ask you about it after.
So now,
No, it's... If you're encoding it, if you're saying if you're modulating the carrier frequency with a digital signal, surely you should have more bandwidth and be able to carry more information. So are they not able to...
no, because all the possible information transferred by a carrier are used for a single channel.
Yeah.
The second channel, there wouldn't be room for it. Plus, it wouldn't even make sense, like reducing the quality or using just the 50% of a signal. How can you monitor it? When you would get a single output. So there is no way to do it. And there is not even much sense having 4 microphones on a single carrier and then dividing them back, it would be super expensive. For what at the end? How can you discriminate which signal is
Well, if you clock
is
right,
what?
if it's clock right, it's the same way it carries on there.
Yeah, but in this way, there are systems doing it. An example, if you think about the 1.8 gigahertz, the DECT is doing it. But you pay a price of 18 milliseconds of latency. So this is not a system that can perform with 18 milliseconds of latency. Nobody would buy it. There is another one. If spectral efficiency is your major concern, eventually you can think about DECT. But for a high-tier wireless system, for professional use, you want to use all the quality, all the possible quality of the RF link to have a maximum robustness and the best audio quality, more than having 4 microphones on a single carrier. So it wouldn't really make sense in this kind of product. If you are doing a video conference call, then it's fine. It's okay not having to manage frequencies or whatever. But in general, except for the DECT that's using a special pattern and it's sending every signal over 3 different frequencies combined with other signals. But except this case, there is no need to add. And it would be a super complicated system, very difficult from an engineering perspective, without any real benefit. At the end, in 8 megahertz, with this kind of device, you can have up to 60 channels on air. So it's a number that is okay for a big show. I really, really rarely saw more than 60 channels on air of microphones. So I think that it's enough efficient, and the target is to make it more robust, more resilient to interferences or to dropouts due because to the fact that you are out of range. So to extend the range more than adding more signals into a single carrier. And obviously reducing the latency is another goal for this kind of microphones, and you don't want to lose it completely to have more signals on a single carrier. So register transmitters. Let's go back. To the presentation. So as I mentioned before, the system now is much faster detecting interferences, and it can align the transmitter and the receiver to change the frequency at the same time. This is meaning that before, with the X-int analog, we used to have to change the frequency. The dropout was about 0.3 seconds, while this time is happening in 25 frames. That's much less. It's actually kind of difficult to notice it, even if you are speaking inside the microphone. Then here we have a charging options, and as I said, there are 2 different kinds of batteries. AD family is using the same as B900 in use for ULXD. It's at least 7-8 hours, 7-8 working hours, depending on the power level and other things. But in high density mode, it's over 11 in example. So they last more than a show or a meeting or even a couple of shows or a couple of very long meetings. There will be different charging docks. The first you can see is the SBC 230. It's very close to the SBC 200 in use for ULXD, but it's for ADX family. It can host a body pack, a regular body pack, or a ADX handled, and differently than the SB200 is in the network. Then there is an 8-slot charger, the 840, and then there is the 840M, that's the charger for the special batteries of a micro body pack. The micro body pack is having a very small battery, so it's the lifetime of a battery is about 4.5 hours. But anyway, enough for the majority of the shows. And for who's familiar with Accent, the XT900 has been slightly changed. New network card and other minor details have been changed, and it's called now SBRC. Shure batteries rack charger, very easy. And the modules are exactly the same modules of the old XT900. So there is intercompatibility in any sense. You can add the new modules to the old charger or vice versa. And all these chargers are network connected, and all these chargers are exactly showing the performances of the batteries. And as we switch on wireless workbench, we can see something more about it. And then the transmitters we have, for who's familiar with ULXD, the chassis is the same. We just relocated the switch that was somehow comfortable if you don't have a nervous talker and you didn't forget to lock the switch. Otherwise, with the ULXD, you can have someone clicking, switching it on and off 600 times per second, and something you don't really like and want. So here is in the traditional position, the switch. And what else? Yeah, it's having, it's here. Okay, wireless workbench. No, I need the KSM8. Okay, for who downloaded the new versions of wireless workbench, you may already, sorry. You may be already aware of some new features that have been introduced thinking of Accent Digital. So the first one, and perhaps one of the most important, is the timeline. Did you ever use it? One yes, two yes. So the timeline is recording what's happening to our transmitter at any time. So we have quality of signal on top. We have 5 bars. Then we have, here we are in quadversity mode. So the 4 receiving antennas And in case an interference happens, we can see it as a red part of a bar. We have a level of 4 different antennas. One looks to be kind of not very healthy, actually. So, how to read this graphic is clear to everyone. How do you consider an healthy signal? What's the level range that makes you tell, okay, this signal is good, or no, this signal is not loud enough? So some of you used it. So this yellow line looks to me like something is not really okay. Perhaps is the omnidirectional? Yeah. Okay. It's the antenna, yeah, A and B are this one is the orange, and this one is the yellow line. This antenna, it's called diversity fin. It's having 2 antennae in one, but 2 connectors. As you can see, 2 cables. The directional is antenna A, and this omnidirectional is antenna B. So one of the two is not performing very well. When it goes below minus 80, it's really a signal. It's really a weak signal. The healthy level is between minus 30, 40, and minus 60, 70, according to the different conditions. Now, I didn't check the cabling. I didn't use any amplifier. Perhaps there is also a little bit of attenuation in the antenna distributor. But anyway, we can consider that this area is okay, but this one, it's not perfect. So perhaps a little more gain would be needed for these 2 antennas to perform in a very safe range. Obviously, having 4 antennas in such a small place, it's super comfortable. Then here, we have information about interferences on this line. We may create one eventually. We have the audio level, and we have a battery life. A. This is pretty cool. If you have to check your signal, and you are in a theater or wherever and you cannot really make noise, this is a very nice tool. You have a tone generator. You have one inside the receiver and one inside the transmitter that can be used to check your levels, to check if the system is working, if it's arriving in the right channel, and even under conditions where you cannot really talk into the microphone. Plus, there is another use. This was the 400 Hertz tone. If you put the 1 kilohertz, is a way to let know everybody that you are in a bad mood and you want to disturb them. Just especially when you have discussions with the operator and you are a stage technician, can be useful to calm him a little bit, or the opposite, to start a fight. Another interesting tool that is in the transmitter, we are going to the utilities, where there are three menus. One is radio, the second one is audio, and the third one is utility. So every time I need, I can send a marker to wireless workbench. Now this, typically when we do our tests, in the ideal conditions, I'm walking around and there is someone else in front of a laptop. And two persons are testing the wireless microphones. That would be perfect, but often that's not the reality. It's already a miracle if we have enough time to walk on stage in the different areas and check what the conditions are. So in this way, I can walk all over my coverage area and put different markers to understand how the system is performing at different points. And when I will get back to my laptop, I will be able eventually to add some notes or to read what was going on. No, I'm not sure. So if I go a little far from the system, and I cover the antennas, I can see that here I had a dropout. Actually, I made it covering the antenna with the chassis of a microphone. That's reducing a lot of the performances of the antenna, because this is metal, magnesium something, lighter than ULXD, but it's still metal. So if I cover the antenna, I see the RF performances going down dramatically. And I can have a full control of the situation all over the stage. The timeline can be recorded as a file, doesn't really take much space, and can be used for our purposes whenever we need to know how the microphone is performing, or can be used for troubleshooting. So we record what's happened and then we find out what went wrong, if something went wrong, or it can be used as a proof of innocence in case someone forgets to switch on the microphone on a desk and is blaming us for the microphone not working. That's happened. So, okay. Now I'm expecting you to have some questions.
The connection between the show link and the transmitters is frequency dependent, or there is something else that allows the show link to identify which transmitter is.
No, sorry, I didn't get you.
See, if I got the show link identifies the transmitters depending on the frequency it's synchronized with the receivers.
No. So every show link can support up to 16 transmitters, and it's completely automatic. So as long as you don't have more than 16 transmitters on air for the show link, if you, let's say I have a show link there and a second show link here, it's automatically managing everything. During the beta testing of a product, Axin Digital was deployed in a Twickenham Stadium for the NFL event, and they were already using Axin Analog, and they added few channels of Axin Digital. Traditionally, they were using 2 show link, 1 per side of a pitch, so like 100 meters apart, and the area was covered just with not drops, but the signal was going a little bit down at the corners of a pitch, where they are opposite of a show link. So during the rehearsal, they replaced the 2 old show link with, and one of the 2 was replaced with a new one, with 2 antennas, and it was so much more powerful that it was the only one connecting to the microphones actually, and the other one was acting just as a backup, but it was covering all the area of a pitch with a single show link. So if you have up to 16 transmitters, 1 show link, if you have, let's say, 2 show links in 2 different locations, it will be completely automatically managed by the system itself. The reason why is that the show link is using a very low bit rate to transfer the data, but the data are sent over 7 times. So it's really slow. You will never download a movie on a Zigbee, but it's really rock solid, and it requires a minimum. Another feature, but it's not new, but it's related to show link, is the capability to read the 2.4 gigahertz spectrum. This can be useful, obviously, for our microphones, but can be useful also if you have intercoms or other devices operating on 2.4 gigahertz. It's acting as a scanner on the 2.4 gigahertz, and if you let this run a little bit, it will end up having 3 channels, 1, 2, and 3, that are the 3 channels of Wi-Fi, and this is the tuning range of the show link. It can be changed manually, or it can change automatically if need be, but usually channel 26, as it's not used for Wi-Fi, is the more safe and reliable, and it's quite rare to see it moving anywhere else. By the way, the tuning range is from channel 11 to channel 26, that are not TV channels, but are the channels of 2.4 gigahertz. And it gives you a nice view about what's going on. Again, here the spectrum is not that crowded. If we were in a hotel with 5, 6, 10 Wi-Fi on air, this spectrum would be much more crowded, and perhaps sometimes we may see this channel moving somewhere else. But all these things are managed automatically, so you don't have to worry about it. And the reason why it was decided to be on 2.4 gigahertz is that it's free of license worldwide. So even in situations where the spectrum is licensed, you don't need to license a new frequency just for show link, because the 2.4 gigahertz is free of license, or it can be used with this amount of power worldwide. We were talking before about the ADX transmitters. One thing that I forgot to mention, no, I didn't want to show this, but I completely closed the presentation. Another thing I forgot to mention is that there are two kinds of ADX handled. The normal one, ADX2, is having the show link control and all the functions we expect from an accent transmitter, but there will be a different version with frequency diversity. So normally, one transmitter, even ADX, will transmit on a single carrier. There is an option of having ADX2 frequency diversity. They made it different because, except for supercritical application, I think nobody really needs it that much. Because now the time used by the devices to move to a different frequency is really, really small, and it's really difficult to notice it. We had some previews at CAPSAT, and to demonstrate the frequency change, we use the spectrum generator. Because talking, even if you do, it's very difficult to notice that anything happened. The ADX2 FD will have two line amplifiers to be able to transmit on two carriers, and these two line amplifiers can be mixed, having a single frequency with super high power. Nominal is 65 milliwatt out of two amplifiers of 40 milliwatt each. That's miracles of mathematics. And so there is also a frequency diversity mode. Now, if you, in your daily business, it's not going to happen, but if you use a quad receiver with quad diversity in frequency diversity mode, you can have a quad receiver that's actually for one channel, because quad diversity is reducing the number of available channels from 4 to 2, and frequency diversity is using two channels of a receiver. So in that case, you have a super rock solid, undestroyable signal from an RF microphone. Then you put a cheap cable and it drops out, but it's not the fault of a microphone. So other questions?
How does the clock sync between the microphone and the
Good question. So whenever we put the audio together, be it from WAV, IF, or any other format, we call it codec. The codec is containing all the relevant information for the clocking as well. So whenever I send out a 24-bit digital audio word, it's not 24-bit, it's actually 32-bit. So the first 4 bits and the last 4 bits are used for the clocking to tell the receiver, the receiving device, what we are receiving is now the sample number 23,000 of this given second. Did you get it was the number 23,200? Okay. So the clocking is included when you encode the audio signal in a digital word is included here. Then, if you are using an external clock, the digital output is resynced to the external clock or to the clock you set up with Dante or ASCBU or whatever. So the clocking is encoded together with the audio. On top of it, the transmitter is sending a recognizable pattern along together with the signal, and that's giving an extra layer of clocking, even if it's not what we properly call clocking, to the device. But this is used only, let's say, whenever you have to swap frequency or there is anything to change, then it relies on the clock of the system itself. Otherwise, the audio is clocked together with the codec. I can't believe I was so clear.
I just have one more question related to LED screens. So you said at the beginning of the presentation that a given LED screen is destroying a given RF radiation, okay? And we can see it in the spectrum. But after they change the content and the color and all, that radiation changes. So how is the approach to work with that? Because if I do one scan at the beginning when the LED screen is on, and I have this selective frequency, okay, this is working. But once they change the content, that's gonna keep working, or?
This is the challenge with LED screens. So first of all, don't run a single scan, but try to keep it as much as possible. So usually wireless workbench can remember several scans, or do different scans during the time, first of all. But more important, you have to work on the antenna placement to reduce the effect of the LED screens at the minimum. It's not always possible, because sometimes you can't decide where to put the antennas. Sometimes you are limited by the length of available cables. So, but always try to use the directivity of the antennas to avoid as much as possible the LED screens. If you have a spectrum analyzer and you walk around even a single panel, better 4 panels of LED screens, and you measure in different points, you will see that the worst part is not the front, it's the back. So the major mistake, let's say this is my LED screen, I place the antennas here, I get all the garbage from the back of LED screen. So always try to play with the direction, with the directivity of the antenna, in order to get the minimum possible amount of RF coming from the LED screens.
The example that he's talking about, is it can be helpful or better if you place the receivers from our house, with facing the antennas, facing the stage?
It depends, but by the distance, first of all. So if you have 10 meters, 15, 20 meters, yes, can be helpful. Even if, in this case, you are using the directivity of the antennas just to go straight to the LED screens. So it's always, I always preferred, but that's not really a scientific approach. I mean, we can talk about different experiences, and at the end, whatever works usually works. But if this is my LED screen, instead of having an antenna pointing at it, I'd rather have an antenna in this, or if possible, even a more directive antenna, to avoid and to reduce the amount of RF from the LED screen that I get into the antenna. Then it depends by many factors. And my recommendation is to keep it in mind and do, whenever you have big LED screens, do at least a couple of attempts. Usually front of house doesn't work for other reasons. First of all, you can't go very high in front of house if you don't have like a layer structure or whatever. And you get much more absorption from all the bodies. And it's kind of risky in case of shows where there is a different temperature between day and night, or between the empty audience and the full audience, because the full audience will sweat and will produce heat and humidity. It will affect your RF transmission, so you may do a sound check in the afternoon where everything is super funky, and then you start the show, and you see the RF level too low, and you spend all your night shaking. So in general, the suggestions for antenna placement, doesn't matter if we have a digital or an analog transmitter, are always keep as close as possible to the transmitters. So distance is obviously affecting, at least in part, the performances. Free line of sight and as high as possible, and with the minimum amount of bodies between your two antennas. Because the bodies, as they are made of water, they are absorbing a lot. Now, perhaps yesterday someone told you that, or if you attended any previous training, the one I did last year or 2 years ago, you have been told the best separation for diversity is about from 1 to 3 wavelengths. That in UHF means from 60 centimeters to 180. That's still valid, but with quadversity, you can add a little bit of fantasy to it. Because having 4 discrete RF lines gives you much more freedom in terms of antenna placement. And honestly, as it's brand new, I don't even have a lot of case studies. But what we saw in some shows in Nashville, where they were working in a very crowded stage, lot of channels, and a lot of LED. So the floor was LED screen, and all the part around was made of by LED screens. Plus, they were in US with a super crowded RF spectrum. They placed the antenna spaced regularly, like 4 meters apart, and they were having super good results. Now, a difference between the diversity of analog systems compared to the diversity of digital systems is that even in the best conditions, when we were combining 2 analog RF signals, we were having, if both of them were good, we were having a better signal-to-noise ratio. Here, if we have only one antenna working under ideal conditions, we are fine. We don't need to worry that much about the antenna placement as we used to do. I mean, we don't have to forget it, but it's we can be more flexible than before. Because there is no benefit having both antennas working completely together. Obviously, it still doesn't make sense to place the antenna one per side of a stage. The diversity is supposed to work to reduce the effect of multipath. So the same signal reaching the antenna in 2 different time slots. But we can be a little more flexible and use a little more fantasy and do some more experiments with the quadversity.
That thing about placement, like in one corner of the stage and all with the diversity, is because of the panning field on the 2 receivers, that the signal is not reaching at the same time to the antennas, and that's the reason why.
Yeah, it will end up having one of the 2 antennas performing much better than the other. So you have 2 zones, but you don't really have a good combination of the 2 zones. And even with the digital modulation scheme and with all the added benefits, it doesn't help, because you have antenna A working and antenna B completely almost dead, but antenna A is still sensitive to multipath. And if you have bad placement, exactly in that moment, you don't have the help of the other antenna pulling up a little bit the RF level, and so you may end up having a dropout or just a bad quality. Now, obviously, when we we talk about RF, we talk about good practices and not so good practices. But there are few things where I would say, no, this is completely wrong. Because there are many scenarios and many applications, and sometimes we just have to do something even if we think it's not the best way to do a certain job, because we are limited because there is a camera there, because they don't want to see the antennas, or because they want you to cover the antennas to be there. So once the basics are there, so right cabling, right gain chain, without overfeeding or without having too much loss in the cable, and whenever you know what you're doing, I mean, there are, as I said, good and bad practices, but there are few things that are really wrong. And the dropout doesn't happen because one thing is not perfect, usually. Whenever I see, I do technical support, and I have customers calling me, hey, the system is not working. So whenever a system is failing completely, usually there is a big mistake behind, or several things are going wrong. It's happened recently to an installation. I was called in Qatar. It was about in-ear monitors. Actually, it was about microphones and in-ear monitors initially. What's happened is one of the two cables was broken. So the antenna A and B, only B was working. And that took not much to be solved. Because when I saw that all the ULXD were working on antenna B only, it was pretty clear that there was a cabling mistake. And the other thing that was happening were dropouts in the in-ear monitors. And the installation was looking quite okay. The cabling was correct. It was a 15 meters cable, nothing special. The distance was not that much, about 20, 30 meters. We tried to find interferences, and everything was looking good. Then finally, I spent some hours there. And then finally, we found out that the major reason of dropouts were an overfeeding the input stage of a PSM. So there were other things not perfect. One of them was that it was a completely open area with just one surface of reflection. This was not helping. And the other thing that was not helping was the overfeeding the input that in the in-ear monitors is creating problems in the RF stage as well. So usually when a dropout happens, it's because many things went wrong. The problem is that we can control some of these things, but there are things we can't control. If the CEO of a company who is paying all the event is holding the microphone like this, there is nothing we can do. I mean, yes, we can try to tell him, and then he will forget. So the idea to have a resilient and robust setup is to avoid that you add one more thing going not as you like and ending up with a dropout. But in general, if you use high-tier systems or even mid-tier systems with a decent setup, they are really robust. And as the spectrum here is kind of clean, you can rely on your microphones. What you cannot manage is a guy holding the microphone like that, or a guy that is like 150 kgs and keeps the antenna on the chest. Then it can really take away a lot of energy and detune the antenna significantly. But Other questions, guys? There is anything you want to see, listen, try to do with the microphones? Perhaps? So, as you can see, it's quite close to the ULXD chassis. It's just more light. Huh? Yeah, when we finish it, yeah.
Hi, I'm Jen Liang Shabu from Shure. We're here in Soldier Field in downtown Chicago, working with the Axient Digital wireless system. Around the world, the wireless spectrum is getting noisier and more congested. Chicago is no exception, as you can see in this spectrum scan. Today we are going to show you how Axient Digital can significantly increase your confidence to operate in a variety of applications and protect against dropouts and other issues, even in a venue of this size. All of the audio you hear is coming from these receivers. We'll use Wireless Workbench to monitor Axient Digital's channel quality meter, which monitors the RF signal-to-noise ratio. For our first challenge, we're going to go to my colleague, Chris Lyons, who is way up in the stands.
Live events today are using more wireless channels than ever, while the amount of available spectrum continues to get smaller. I'm wearing an Axient Digital body pack set to high density mode, which enables you to use up to 47 active transmitters on just one 6 MHz TV channel. And even though high density mode transmits with a power level of only 2 milliwatts, it's still more than enough to cover even a large venue like this. I'm more than 150 yards away, and I'm still being picked up perfectly, even though the body pack is behind me, without a clear line of sight to the receiver antennas.
Thanks, Chris. So far, we've been using 2 antennas with true digital diversity. However, many productions have complex stage setups that involve more than one area of the venue. So for our second challenge, we're going to move off the field and into the tunnels of the stadium. Quadversity mode allows you to attach 2 additional antennas to the quad receiver. We've placed 2 additional antennas at the front of the tunnel. Come follow me. The Axient digital receiver intelligently monitors and digitally combines the signal from all 4 antennas. Quadversity can increase gain and signal stability across a single zone or extend the range into multiple zones, just like this concrete tunnel inside the stadium, where I am transmitting clean and clear audio. And now I'm going to send you to Michael Johns, the product manager for Axient Digital.
Operating wireless microphones is all about signal-to-noise ratio. We've designed a digital radio that requires less signal-to-noise in order to operate. As a result, Axient Digital provides signal stability in a way that no other system can. I'm currently transmitting from this handheld at 10 milliwatts to our A and B antennas. For our last challenge, we've identified a noisy frequency and tuned this handheld to transmit directly on top of it. As you can see from the spectrum analyzer, there's a high potential for interference. However, Axient Digital is still receiving my signal perfectly. I am standing on the other side of the stadium, in the middle of downtown Chicago, operating on top of a noisy frequency and still passing flawless digital audio. Now that's integrity you can hear.
Up to 1,500 life cycles, and they are still over the 80% of the health. So that's what we consider okay. Below 80% is not that good. And I mean, 1,500 is like, yeah, because the guys again were like, yeah, they have some other things to do. A guy started every day doing the same routine, started the battery, and then we started completely overnight, and then the next day after 2.5 years, we started getting enough. But we can consider 1,500 complete life cycle as a realistic number. Sometimes thinking 1,300, some other times can be 1,800. On top of it, all the network recharger have a function that's called storage mode. In case you don't use your batteries for 2-3 weeks, let's say you ship them from here to Baku for an event, and it takes 2 years plus the custom, blah blah. This storage mode prevents the battery understand the life expectation of batteries. As I said before, I think we are having the 80 series powered by the traditional LP900 batteries, while the 80X series is having different batteries. The reason why is that they didn't the ST900 is perfect replacing two AA batteries, but for 80X, thinner and slimmer and smaller and lighter, they were too big. So they decided to use batteries that are similar to the old accents for some things, but the enclosure is completely different. The old accent system was not having any IC rating. Here everything is having an IC rating. Perhaps there is better because I will try to type button. I don't know what it is. You see even the body control filter that transmitter that's around, you can see that the kind of flows and even the on-off switch is different than what we had before. Just consider that the samples you have in hand are pre-production samples. Minor things. Don't worry. Even for the informal chat after the training, it's better if I have a microphone. Okay? The samples are not finished products yet, but the modifications are really minimal. And what's gonna change, not only from now to the moment where it will be available, but even after, is the software part that can be updated constantly, as it happens for all the major Shure, all the high-tier Shure products. All the changes that can happen are all the improvements that can be done on a given hardware. But perhaps they are taking a little more time to be developed, or just to identify that there is a need for a certain thing. Then all these things are happening with firmware updates. This is why every 6 months, less if you have a big inventory, my recommendation is to check Shure Update Utility. You connect it to internet, and you download the latest firmwares available. When there are updates to download, they will appear here, and you will be able to download the more recent software and the more recent firmwares for your devices. Sometimes are just small changes, small thing. And in this case, like there is you move from 1.17 to 1.19. Some other times the changes are more relevant, more radical. In that case, it's called a major firmware update, and you move from 1.x to 2.x. Be careful doing it for 2 reasons, and always read the release note of a new firmware. In example, there is a new version for ULXD. In the release notes, there are 2 clear advices. One is that once you update the receiver, it cannot operate anymore with one. You have a receiver on 2.x, you cannot operate a transmitter at 1.x firmware because there is a change in the modulation scheme. So there is no intercompatibility. So if for any reason you can't update your transmitters, don't update your receivers as well. And another thing that was clearly mentioned, but nobody really reads the release notes as long as everything is fine, is that Shure ULXD 2.x was not compatible with Shure Plus Channels apps. So personally, I'm waiting for the new release of Shure Plus Channels app because I know they are improving it in a way that I will like more than now. Now mainly it's a control app, a monitoring app. You don't really use it for frequency coordination or this kind of thing. And it's not really, if you have many channels, you can see them one per time. It's not really super comfortable. And if you only have 2 channels, most probably they are very close to you. So you don't really need a Wi-Fi router and an app on your mobile. Anyway, it was clearly stated that Shure ULXD 2.x is not working with the existing version of Channel Plus, and I received at least 10 emails. Why? I updated the firmware and it's not working anymore. So read the release notes. Obviously, I mean, if you have 2 channels of UHFR to be updated or 2 channels of whatever, it's not a big deal. If you start having 40, 60 channels and you need to plan the moment in the season also to do your updates because it may take a little time. Like one request that I had for the engineers was to remove the need, and I was showing my complete ignorance on this. When you update the firmware of a transmitter, it happens via infrared, right? Whoever experienced it. Okay, guys, honestly, did you suffer a little bit? Yeah, me too. Because it's long and you're not really always comfortable with it. So the request was, guys, sorry, why don't you make it, at least for ADX, via 2.4 gigahertz? And then they started a long explanation why it's not really possible. Because via infrared, it can memorize a certain amount of information. And then once all the software is uploaded, it reinstalls the operating system of a microphone. The wording is not perfect, but and it can be done in different blocks, and this is the reason why often you have like from 1 to 40% super fast, and then 40 to 70% you sweat, and you are afraid that something is not going properly, and then it goes smoothly again. Because there are different blocks, but it actually, because of the way it's built, it wouldn't be possible to memorize all these informations if they are coming via Zigbee. And it will take forever. While even if it's not comfortable, infrared is faster. The face the engineers did when I asked this question was like, you think you are original? We heard it 200 times, but it's not that easy to do. But it's something that one day will be possible, perhaps, because I think it's not a weak point, but you have to do it not on site, not 1 hour before the show, possibly not even 2 hours before the show. And sometimes you are forced to do it because it's happened recently on an installation with the equipment coming from different rental companies, and they were at very different firmware levels. So someone was having a very old firmware that was not compatible with the latest version of Wireless Workbench. That was needed because some other rental companies were having a last update of a firmware that was not compatible with the older version of Wireless Workbench. So in general, do your housekeeping. Summer is coming, season is going slower now, I think, for everyone. And my recommendation, this is the right time to check your inventory, check the firmware version you have, update them if needed. If something goes wrong, you can always call me and complain. And I promise it's true. Friday morning, couple of months ago, I had to go on site because a colleague and I'd say also a friend, but that doesn't matter. Anyone can call me, even on Friday morning, was having issues updating a bunch of ULXD. So we, as Shure, offer support. But in general, if you read the release notes, it's much more easy because most of the things are written there. Like you cannot update ULXD 1.5x to 2.x. You need a step in between, and there are ways to do it because now it's very difficult. Okay, if we go here, Accent distribution amplifier. Sorry, it's a little bit complicated. You can decide at any time to put down or up your firmware version. So you have at least four different firmwares inside the app. So if something for whatever reason goes wrong with the 1.17.10, you can always revert back to 1.16.11 or 1.15.3. So you can move on or even go back in the firmware versions if need be, to have always a good compatibility with all the different devices. UHFR will not be updated anymore. ULXD has reached now a 2-point-something version. Okay, 2.0.28 is the last one. And you cannot update from 1.5, I think, 0.6 VA, if I don't yeah, from 1.5.6, you cannot move directly to 2.0 point whatever. You have to do a step in between. This is mentioned anyway in the last release, because changing all the programming on FPGA on the FPGA at one time is a little too risky. So the transmitter in that case will give you FPGA error mistake, but can be easily recovered, downgrading the firmware of a transmitter to, let's say, 1.6, 1.7, uploading the firmware 1.6 or 1.7 to the transmitters, and then putting up the firmware of a receiver again, and putting up the firmware of a transmitter again. So if you don't do it in one step eventually, but in 2 steps. Just for ULXT 2 point whatever version, because usually all the other firmware don't have this kind of issue. Any question? Any stress test for a microphone? Do you want to hear it, test it? If you want to check inside the menus to see, hidden features I forgot to speak about. or curiosity. Okay. This is something you will not have. Okay, I don't have it as well. Ah, okay, something I really forgot to mention. One nine two 168 124 116 124.
See where it says rack ID background? Does that change the color of the screen?
Sorry?
Does the rack ID background change the color?
No, this is just an app.
See where it says white label, white tape, gray?
Yeah, but this is just regarding the app.
All right.
That's called Rack Proxy Server, Rack Proxy Unit, and it's an application built by one engineer at Shure who became father during the beta testing of the alpha testing of the unit. So he had the parental leave, he was allowed to stay at home, but he was running some testing. So he built this app just to monitor the units from home. And we all loved it, so it would be nice for it to work. It was working before. Let's see if I can. Yeah, so it's not even really supposed to work, and actually for some reason it's not working. Found. Nope. Let's see if a hard reset. If not, I will show you the same thing. So what I mentioned before is that you can use the digital wireless receiver as a Dante receiver. And it has two very nice and interesting things. Yes, now it's working. Whenever something is not working, networking or whatever, switch off and on and perhaps it will help. An engineer may tell you a better reason, but at the end, often it's working. So it has two Dante features that before we go back home, I'd like to show you. Okay. Now the first one, I just pressed the headphone volume button and I reach this menu. But I need to switch on again my Dante virtual sound card so I can give you at least
coffee break session is on.
now we 5 minutes and we are done. If we don't have any question, it's coffee and bye-bye. Okay. Now I have this thing playing. And here, the device is scanning for any other Dante source in the network. So I have my ULXDs, my laptop, now here I don't have anything connected, but I know there is an headphone back there. Yes. We should hire a model. So I'm listening to my laptop through the headphones, and I can, obviously, this is really helpful when the show is very boring and you want to control your microphones, listening to something better than the bullshit they are saying. That's an option, but I don't think they made it with this thing in mind. Most probably, the interesting part of it is that you can monitor your signal path at any point. So from the stage box, input of a console, output of a console, or wherever you feel like in your Dante network for troubleshooting, even without involving, in example, the operator at the console that may be busy doing something else. If I think about sound checks with 24 musicians with in-ear monitors on stage, I can really see the need of this kind of troubleshooting tool. And another possibility is Dante Q. Now, today we didn't do many demo, like exciting things and wow effect, and this will be the minimum of excitement. You have just to imagine it, because with one transmitter, with one receiver, it's not really that big thing. But if you imagine to have a big rack with 20, 30, 40 channels, then this function makes much more sense. When you go to Dante Q and you set your device as a listening station, now I don't have other Axion digital devices, so that can participate. It's searching. Say, listen, there is nothing else. But if I have more receivers, just pressing these buttons, I would have the cue on my headphone output. Doesn't matter if it's the first receiver or the channel number 40. At the end of a rack, I will be able to listen to them, selecting with these big buttons without moving the headphone jack. I know, if you have only one, it's not that great. I understand. Like, okay, who cares? But if you think of having multiple receivers and show is starting and you want to quickly check that all the microphones are okay before going on air or people going on stage or whatever, that can be really an helpful tool. There are manufacturers that are doing just listening box. So they connect everything and they have all the buttons just to preview all the different microphones without patching the cable several times. So these are two of the multiple features that we have. The menu structure, and then after this I think we can have a coffee and consider our training, our session concluded if you don't have other questions. So if you have some, please. There is a device configuration, so RF, audio, device naming, network configuration, locks at different level, fan, display, this one can be inverted. If it's in a very dark room, can be helpful. Otherwise, I think nobody would like to have this super bright LED screen on stage. There is another exciting function that's display sleep. Now, if I don't touch if I go out from the menu and I don't touch anything for 10 seconds, the display will go to sleep. So it will become completely dark. It's perfect if you want to have an heart attack, you go back to your racks and everything is dark, like this. Again, the purpose was not to kill your colleagues when they did it. Most probably is because in some theater, in some application, even the small lighting can be disturbing. So this is perfectly black, just these two buttons to keep your heart working. And then there is a per channel configuration where you can edit different parameters. One is the complete gain. From the gain is not the gain of a preamplifier. It's not actually a gain. It's more a volume or a digital trim, because the system has its own gain. So it's considering everything, converting with the best signal-to-noise ratio, and then once it reaches the receiver, it's brought up or down according to the need, and it's linear and consistent with all the different levels you can apply at the input stage. But then you can add a digital trim for every and each transmitter. Now, if you see below, I have a second register transmitter. So this is the first one on air. This is the second one. But I can access only when it's online. And I can have up to 10 registered transmitters per channel. Basic case that comes to my mind is when you have a guitar player, is obviously having one receiver, but one different transmitter for every and each guitar. Now, Gibson with the super active pickup will have much more gain than another with small, I don't know what, when an acoustic, yeah, it depends, or two different acoustic guitar, one with active pickup and one with non-active pickup, whatever. The idea is that you can have a consistent level out of a receiver, and you can digitally manage this different gain to have a consistent output. So you can have up to 10 different not available frequencies, 10 different transmitters, let's say 10 different body packs, connected to the same channel as a registered transmitter for the receiver. So if you have, obviously you can't switch them on at the same time, one per time, as it's always been with the guitars, but you can have up to 10 registered transmitters with their setting. Another thing that I don't remember where it is. Yeah, you can have user presets. Let's say today I have a show called show number 1. And tomorrow I have show number 2. But then the day after tomorrow I have show number 1 again. I can purely have different presets for the two shows, and just with one button I can recall each and every setting for the transmitter, for the receiver, and for the related transmitters eventually, if I have ADX transmitters. So names, settings, gain, color, whatever. I can instantly recall the status of a device or different status of a device at any time. No, there is no EQ function. No EQ. Reason why? We think that this system is going to be connected to a mixer, probably a decent or good one. So we didn't think that it was a kind of added value having an EQ for what? It could just create more problems than benefit. But if you think that an EQ is a good idea, you can always speak with the engineers so they can tell me bad words, or why what I'm asking is not to be asked. Okay, I will. Device RF, I can limit the RF band. I can encrypt. I can have transmission mode standard or high density. Quadversity. Quadversity is one of the cases where the device needs to restart. If we, let's say now we are in quadversity mode. If I want to go back to normal mode, the device has to reboot. Now I'm kind of sure that I'm losing the connection over there. Nothing. The rest, the device is here, If you want, come, take a look. If not, there is a coffee, bye-bye. Yeah. That was for surviving with the jet lag that I have, right?